So ready? Yeah. Malcolm McDonald is the director of the Applied Space Technology Laboratory at Strathclyde and a visiting professor at the Center for Space Research at University College Dublin. He's also the director of WeatherStream, which is a US-based weather analytics company. He's in the advisory board of Seraphim Space, which is the world's leading specialist investor in space technology. He was a non-executive member of UK Space Agency Steering Board until 2020. Currently the vice chair of the agency's Space Technology Advisory Committee, and his work developed concepts in and applications of space technology by developing research into astrodynamics, network systems, swarming, distributed and collaborative systems to advance new concepts in the exploration and exploitation of space. So currently he's recognized as one of the top 2% globally of engineering researchers. So without further ado, I'll give it over to Malcolm to talk.
Okay, thank you for that introduction. Assuming you don't interrupt me, then I will assume you can see my PowerPoint slides. So I wanted to just start, for those of you who are not perhaps as familiar with the University of Strathclyde, and give you an overview of the university itself. The university is located in the centre of Glasgow, and it was founded in 1796. So I like to think of Strathclyde as the first modern university. There was, a couple hundred years between the ancients being formed and then Strathclyde being formed. And it was really the start of a lot of the newer, more modern universities being formed. And this was right in the heart of the Scottish Enlightenment period. And so the idea of the university from its core was this idea, from its foundation was this idea of a place of useful learning. And you'll see that narrative flowing through my talk today. And so the mission is to make a positive difference, both to the students, to society, and to the world. And I'll try and show how our research does that. It's good to put the talk into some context of the broader work that we do within the lab. So I lead up the Applied Space Technology Laboratory. And what we're looking to do there is to address global challenges, working at the boundary between different disciplines and using those learnings from one discipline in order to move innovation forward in different areas. So broadly speaking, we break our research down into 3 areas. We've got a lot of work on Earth observation. We've got a lot of work on spacecraft technology, particularly CubeSats and small satellites, and then a lot of work on network systems. And there we're trying to develop insights into network systems across the natural sciences so that we can then engineer better connected and more efficient space systems. And that's really the ethos of the talk that I'm going to go through today. So at times it might feel like I've gone off on a very weird tangent and I'm talking about things that don't seem at all relevant to why we're here today. But stick with me and we'll bring all that back around to space systems and you'll understand how we go about the research in the lab. So one of the key tenets to what we do is we seek analytical solutions to any problem that we address. It doesn't mean we don't use numerical systems, it doesn't mean we don't use machine learning, but we bring them in at a time when we can't go any further with an analytical solution. So we're clear that they're adding value and we're not just throwing, for example, artificial intelligence at a problem because it will give us an easier answer. So we're looking very much at that idea of understanding the physics behind a problem or the mathematics behind a problem and then developing it from there. So looking at network systems and swarming systems, looking back at the work we've done as an example, so I can look at the fragmentation problem and when does a network or a swarm fragment? And you can measure that looking at the Cheeger constant. And the Cheeger constant really is just telling you how choked the communication graph is becoming. And as that Cheeger constant scales up, or as the size of the network scales up, then the Cheeger constant tends to 0. And so we did some work looking at how you can analytically estimate that, because it's quite a numerically complicated thing to work out. So we came up with this analytical formulation that tells you what the minimum possible bound can be for the Cheeger constant. And so that then allows you to see that as the network size grows, then information on the size of the network has to travel faster and faster through the network to avoid fragmentation of it. And that applies to a swarm or to anything else. So this allows us to start to get some insights into how you would go about engineering a system and how you would understand what's required to stop it fragmenting into multiple networks or multiple different swarms. And why that information is important is because when you start to look at taking a network from one state into another, and so this can be applied to anything. It's really easy to think about it in terms of like a Starling fork or something like that, but it can be, taking a room from one temperature to another. So what we're looking at here is how do we take a network and allow it to react to external stimuli and analytically allocate where the resources should be for that. So if we take a really simple example here, we've got a simple lattice network. And if we look at different ways that we can allocate the resources to each of the nodes within that, so we move from state 0 to state 1. So the green bars on the graph in the center of the screen, that is looking at just a simple uniform allocation of resources across the network. We've then got a numerically optimized solution in blue, and we've got our analytical solution in red. And what we're doing there is we're treating the system as a dynamical system, taking the eigenvalues of it and the eigenvectors, and using that to extract a control vector, which we then allocate as the resources. So it's fully analytical. And you can see that the numerical method and our analytical method give very similar insights. And the uniform method with this, if I can find my pointer, this very low green line here is much slower to transition from one state to another. And we can look at that in different types of networks. We can apply it to a small world network. We get a similar type of relationship. And again, with a random network, we get a similar relationship where the analytical and numerical method are performing very similarly. And what you're again seeing is that the uniform allocation is quite rigid. So what you're seeing there is if you treat a network evenly and you give everything equal resources, it's quite difficult to move that network or that swarm from one state to another. But the other thing that we're starting to see here as well, and I'll come on to this in the next slide, is in this allocation here, we are seeing an allocation of resources from the optimizer across two different nodes, whereas our method only found it on one node. And I'll come on to that in a moment as to why that starts to become important. So this work, again, is allowing us as engineers to think about how we can engineer a network or a swarm and move it from one state to another in a rapid fashion. And this is similar to things like a flock of birds, where we know what they're doing, but we don't understand fully how and why they're working in that way. So I was talking there about that split of allocations in that random graph there. So if we take a network like you see on the screen here, and you've got to identify where are the leaders within that network? What are the influential nodes? How do you go about doing that? Well, the approach that we take is that we translate that into a dynamical system. We perturb it, and we look at the eigenvectors and eigenvalues of that. And that's what you see in the two graphs in the center of the screen here. And what we've done is we've taken the first three eigenvalues and we have plotted those in a three-dimensional Euclidean space. And what you get are these lines or communities coming away from the origin of this graph that we have created. And each of these lines or branches that you see color-coded represents a different community within the graph. But more than that, the nodes that are furthest away from the origin are the most influential nodes within each of those communities. So now, analytically, and quite simply, we can identify communities within the graph, and we can identify the key leaders within that network. And in terms of a comparison with a computational approach, there's more than an order of magnitude reduction in the computational effort that's required to deliver this insight. So you take all of that, and I've mentioned Starling flocks already. So let's have a think a little bit more about Starling flocks. We've done a lot of work looking at dynamics of network systems, We've applied that to looking at, identifying individual leaders and understanding the structure of that network. So we know that a starling flock, each bird follows approximately 7 of its neighbors. We don't really know why. There's a lot of literature suggesting that it's because of the cognitive ability of each bird is limited, but logically that must have been what has evolved. Why has it evolved in that way? And we don't really have that insight. So if we think of it as an engineer, and you think, okay, this is a network, they're all following about 7 of their key neighbors. Where would I position the key birds within that flock so that they could identify that there's a predator coming and trigger a response to it? Well, logically, you would put them around the edge. You would put them at the edge of the flock so that they can see outwards. If all those key birds are in the middle and all the other birds are looking into those birds, the predators coming from behind them, they're not going to see them. So there's a logical, intuitive answer that you would expect to get. So we looked at the system dynamics to reveal the most influential birds within that network that would lead it from one state to another. So we're looking for rapid consensus here. So if we allow each bird, so this is just a numerical simulation, and if we allow each bird to observe 100 other birds, all of the key individuals are in the center of the flock, exactly where we wouldn't expect to see them. We drop that down to 50, then we start to see them spreading out. And by the time we get down to 7, you can see the key birds are spread throughout the flock. So what we're seeing here is that that low out degree, or the fact that each bird is only observing between 5, 6, 7 of their key neighbors, that is the key thing that allows a starling flock to react in such a fluid and dynamic and unpredictable way, and makes it so difficult for a predator to actually catch any one of these birds. And ideally, what the birds are looking to achieve is to drive that number down as far as possible. But if they start to observe too few birds, you then start to get fragmentation of the flock because the information isn't moving quickly enough through the flock. So we start now to have that understanding of how we can start to use this knowledge in our engineered systems. We've taken this a little bit further as well and looked at other areas of the natural sciences. So we've done work looking at neurological conditions where we're looking to identify regions within the brain and understand how things like mild cognitive impairment and Alzheimer's disease, how they impact the human brain and the function of that brain. And again, applied these same algorithms that I've been talking about to identifying these key insights to what's happening within the human brain. We've also applied that to identifying autism in really young children as well. So these are really diverse areas of study that we can take those learnings into our space systems. Very quickly, I'll talk about this one. A couple of years ago, study of contagion within a population became quite fashionable. You've probably heard of why. So we started looking at this as well. We thought, there's a bandwagon, we can jump on that one too. And we wanted to understand effectively, what is the definition of an effective spreader? What makes somebody an effective spreader of a disease within a population? And the conclusions that we came to was that there's actually a trichotomy of definitions of effective spreader, and it depends what you're trying to achieve. If you want to get a very rapid initial spread through a population, that's one type of effective spreader. If you want to get quite a linear spread through the population, it's a different person within the network you want to contaminate. And if you want to get the entire population infected as fast as possible, it's a different person. But these 3 individuals, or those 3 nodes within the network, are mutually exclusive. You cannot achieve all of them. So the definition of an effective spreader depends on the disease, and it depends on how you want to, or what you're trying to get through the population. So using all of these insights from the natural sciences, we then take that over into our space engineering research, and how can we use that to advance what we do. So we started looking at the resilience of space systems, and particularly the resilience of interconnected space systems. So if we look at just a constellation without intersatellite links, then it's a relatively simple 2-state relationship. They're either fully operational, each spacecraft, or something fails and you move into a failed state. If we introduce inter-satellite links, then it becomes a much more nuanced scenario and a much more graceful form of degradation. So here, we're just applying a Markov chain to look at the probability of being in each individual state. Now, what you see is that you are less likely to be in a fully operational state because the spacecraft has become more complicated, but you're also far less likely to be in a fully failed state. So, for example, if the inter-satellite link fails, you go back to just the scenario we were in previously. If the payload fails, then your spacecraft can still transfer data from other nodes and it can relay data down to the ground. So you've got much more graceful degradation when you've got this interconnected networked system of spacecraft. So that then led us through to a range of different work looking at delay and disruption tolerant networking, where we're looking at how can we move data through a constellation of spacecraft and do that in a near optimal fashion without having some sort of oracle that knows where everything is and knows what is happening. So we've developed a range of different algorithms to address this. And what we're really interested in here is how do we integrate both ground, air, and space systems, and how do we move that data around in a really efficient way? And the simple thing to think about to understand the problem here is, I've got some data, I want to get it down to the ground. Do I pass it to the spacecraft I can talk to now, or do I wait and pass it to the next spacecraft? And how do you know which is going to be the better outcome to that problem? So that's the essence of that work that we've been doing. And that's led us to a lot of work looking at the kind of agile and responsive space systems. So for that work, again, we're looking here for an agile space system. So we started from the basis that both for an agile space system, you need to have maneuverability. You need to have a spacecraft that can maneuver. And I'll come on to show why that's not actually required. So we started here. We're looking at a scenario of an earthquake in LA, and you've got an asset in something like the same orbit as the space station. So analytically, you can quite easily work out that, okay, we're going to get a couple of observations of LA. There's then going to be a 12-day gap until we can see it again. What can we do with this agile space system? What maneuvers can we perform to reduce that 12-day period? So again, fully analytically, we can come up with this oversight of all of the different all of the different options for those maneuvers. So you can see each solution gives you actually a range at each time. So just below 2 days, there's a range of options there, from very little propellant being used up to kind of 15, 16 meters per second. And if we look at that in more detail, what you're seeing there is a range of different look angles. So if we choose to burn only 1 or 2 meters per second, we could see LA, but it'd be right on the horizon. So it'd be a really rubbish view of it. Whereas if we go up to 16, 17 meters per second, we can get a look angle of about 45 degrees and get a really good view of the target region. So we can then scale that up to looking at constellations of spacecraft and how can we address constellations of spacecraft as a networked system. So here we're looking at what's the benefit of having a static constellation versus an agile constellation. You're looking here at 4 different national parks in Scotland, US, Mexico, and South Africa. And you're looking at the benefit of being able to maneuver those spacecraft in a coordinated way, treating that constellation as a networked system. And you can see in each of those, you get an improvement in the persistence. You get more time overhead each of these different targets. And because it's a network system, you can play different games. So we can target subregions within the target. We can do fuel balancing across it and that sort of thing. But I mentioned that this is all with maneuverable spacecraft. And one of the things that we started to understand was maybe there's something more intelligent that we can do. So keeping with the idea of an agile space system, what you're looking at here is the last reported location of all ships in the world in a 24-hour period in August 2019. So the little pink dots are land-based receivers, and all of the black dots are space-based receivers. So these are data from satellites. And what we're looking at is where would be the best place to put our ground stations to get the data from the detection of the ship through to the user within the required time frame. And this is a challenge where there is a regulatory limit. Your data is of no use if it's more than a certain age. The traditional approach to solving this problem is an algorithm called maximum flow. It's quite a greedy algorithm, but what it does is it maximizes the amount of data that comes through from all of your targets. The challenge with that is if you've got a target that's quite difficult to cover, it'll pretty much just ignore it because you're not going to get a lot of data from it, and it can be more efficient if you want to maximize your data to just forget about that node. But where you have a regulatory requirement for guaranteed coverage of the whole of the Earth, you can't do that. You can't just throw away those bits that are just a bit too difficult to deal with. So we decided to treat this problem as a consensus problem, where we could treat it as a network that we want to move from all of the targets from being unobserved to being observed. So we've got consensus of observation across all of the target regions. So we simplified the targets down to the blue dots that you see on the screen, and we're looking for what's the optimal ground station selection from a deck of about 95 ground stations. Where should we pick those ground stations to make sure we get all of the data through from the system? So the blue crosses that you see on the screen, a bit like that one there where my cursor is, those are the ground station selections if you want full global coverage. But then if you say, well, actually, what I want to do, I want to just prioritize the Caribbean, and I don't really care about the rest of the world. So that is the targets with the blue dot with the wee red circle around them. And in that scenario, the ground stations move to different locations, and those are the red crosses that you see. So very quickly and analytically, we can tell you where are the correct ground stations based on your different priority regions around the Earth. And what this now gives you is the ability to have a very agile space system simply by turning on and off different ground stations. So the spacecraft are still in the same orbit, no spacecraft has moved, but we can prioritize different areas on the Earth and have different performance of our constellation of spacecraft simply by turning off one ground station and turning on other ones. So I mentioned that one of the things about the university is that we like to make our research useful, and we like to take it all the way through to application. So we've been working with ESA and with Clyde Space to take all of this research right the way through to, hopefully, through to flight. So we're working with them on a ESA Pioneer project called Expansion. This is approximately a 20 million euro project. And what we're working here is to take through all of those different algorithms we've been developed around ground station selection, ConOps of the spacecraft, the disruption and delay tolerant networking that we're working on, working with companies like Bright Ascension to develop the onboard flight software for that, bringing in things like the bundle protocol, so that we'll be able to then deploy that onto a constellation of spacecraft that will go up in the next year or so. And we'll then have the flight data of what actually happened with this ship tracking constellation. How did it behave? How was data routed through it? How were different data bundles fragmented? Where did they go to? What decisions did the spacecraft make? And we'll be able to gradually increase the level of autonomy on board these spacecraft so that we'll go from having quite a lot of human interaction to more or less pushing all of that autonomy up onto the spacecraft. We'll then be able to get that flight data and see if the spacecraft are behaving in the way that we would expect them to behave. So this is quite an exciting project for us, quite a different project, and it's really that start for us of moving towards kind of large networks of cooperative self-organizing spacecraft. And I think that's really one of the key things that is of interest to us, and some of the work that we're going to be moving on to do in the future is how can we have these very large networks of cooperative spacecraft that work together and that move a lot of the very manual processes that we have just now through to having a much more automated space system in the future. So with that, I will wrap it up and hand back over to the room in Surrey. Thank you for listening.
Any questions from the floor? Or online? online. I can check if there's any questions online. So I might ask one question here about, these look like very forward-looking designs of like the Matryoshka orbital networks and things like that. So how far ahead do you think it is of current architectures? When do you anticipate some of this would be in reality?
Well, I mean, so the work that we're doing with Clyde Space on the expansion project, those spacecraft are through CDR. So those will be launched in the next year or so. Clearly, that is not at the more complicated end of what we're doing. But I wouldn't think it's not that far away. And the notion of having much more increased levels of autonomy on board your spacecraft is really it's a fundamental requirement as we see the size of constellations go up. We were hearing yesterday from the guys at CGI about how they couldn't just do what they normally did with the operations of OneWeb. They had to change things. They had to transition to something different. And we're going to see that increasingly with other constellations as well. As just the number of spacecraft go up, we're going to have to look at doing things differently. And a lot of the disruption to late order networking that we're interested again, you're seeing that coming through with things like LunaNet, which I think is the next talk, where there's a fundamental requirement for this type of automation and this type of intelligence to be embedded into the space system. So I think we'll see it emerge over the next few years.
Okay, thanks. I see, I think it's a comment possibly about one of your earlier slides that something looks like a Blanusa snark, which is a particular kind of graph. Dave Tat, do you want to, was that just a comment or would you have a question around it that you'd like to ask online? You can unmute yourself if you like.
Yeah, early on there was a connected graph that looked exactly like a Blanusa snark, and it's like, is there any applicability of that sort of graph type for thinking about connectivity and bandwidth in this case?
I realized I was muted. I think that was just a coincidence. I don't think that was by design. I think most of the work that we look at tends to be, we're just looking for things that work across different networks. We tend not to be looking at specific types of networks and their applications. Although it is always interesting to think about, is there something specifically applicable that we would then want to push the design of an engineered system towards that. But I think in that instance, I think that was just a coincidence.
Cool, thanks. Any other final questions? We have time for possibly one question from the floor. If not, let's thank Malcolm for the talk.
Thank you.
We'll probably have to have a slight switch of the program because looks like Dave Israel is having some trouble with his connectivity now. So what we'll do is go over to the lightning talks. We had 4 lightning talks. We'll do 2 of them before the break and then go into the break, and hopefully they will have connectivity after the break and we can come back to the other 2 lightning talks. So Gili, your talk will be in the lightning talk session. We'll do the other 2 ones now. So yours and Chris's talk we'll do in the lightning talk session itself, but
next one.
Right after the break, I think. Yeah.
In the last one.
Yeah. Yeah. After the coffee break. So I'll think. Yeah. 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 Thanks. So this was the lightning talks are mostly about work that's happening in various departments here at Surrey, and so the first of those is going to be Muhammad talking about his work, looking at measurements. So what we've been doing is measuring actual Starlink networks in people's homes. So we've got some kind volunteers who have basically installed a browser plugin that we have, and some who have also plugged in a Raspberry Pi that we have shipped to them in different countries. Over to you.
Okay, so thank you for joining us again. So here, yeah, today I will present our paper under submission. It's a browser side view of the Starlink connectivity. It's a measurement study on Starlink performance. So yeah, I don't want to repeat that. We talked about that yesterday a lot. So we know the internet from space like years ago, like 45, 50 years ago, when we start sending geostationary satellites to the space. But the problem of these satellites is that they are very far away from the Earth. So the latency that they can, to send a signal or to send a packet to these geostationary satellites and go back, it's something like around 200 milliseconds or half second. But recently, in the last five years, from 2018, we started hearing about the projects from Starlink and OneWeb to send thousands of LEO satellites to the space in order to provide not just low latency connectivity, but also high bandwidth and enabling another new type of applications like something cannot be provided now by existing fiber infrastructure that require very low latency. So motivated by that and motivated by the fact that we are into this mega consultation areas, which is motivated also by the fact that there's a lower launching cost and there's a race to send 10,000 of these LEO satellites, enabling, as I said, new application. We thought about what if we start doing like a first look at the performance of the only existing commercial LEO network, which is Starlink. So in this study, we're trying to answering some of the few research questions. So for example, how does Starlink connectivity compare to existing ISPs in the same geographical location? So does the connectivity quality change from one location to another? And how the weather will affect the performance of Starlink in terms of latency? And for any measurement study, the key part is how we collect the data set for that measurement study. So we have two kind of data set. So we have browser extension data set that we developed a web browser extension, and we ask users, Starlink users and non-Starlink users, to install that browser in their to install that plugin in their browser and start reporting the performance of their connectivity. So what we are measuring, we're actually measuring a page load time for any web page that the user visit. And we also randomly picking top websites from Tranco list. And we measure again the BLT, the page load time. And we have another data set, which is actually an active measurement data set. So we have volunteers in 6 different locations, but that study was, we only had 3 at that time. So this distributed over 3 different cities, London, Barcelona, and US. So we asked them to host a Raspberry Pi, and then on that Raspberry Pi, we collect measurement like throughput, latency, packet loss, relying on the existing pin pipe architecture of Starlink. So what we do is that the Starlink comes with a dish and the router, as we saw in the lab. We just attach a Raspberry Pi to that router, and then we have a scripts here to collect the measurements that, as I described, and then Starlink can just do like a pin pipe to the nearest Starlink gateway. So overall, we have like 18 Starlink users using our browser extension. We have 10 non-Starlink users. They are distributed over more than 20 cities and 3 continents. And until now, we have records in the database around more than 50,000 measurement samples, mainly page load time. And also, as I mentioned, we have another 3 volunteers where we do active measurement on their Raspberry Pis. So I'll just go straight into the result that we had. So trying to answer the first question, how that compared to the existing ISPs. So here I'm presenting on the x-axis. I'm presenting. So what we do is that it's like a trace route experiment. So we have a virtual machine hosted on a Google Cloud in North Virginia, and then on a single location in London, we have a 3 connectivity. One is a Starlink, and one is a cellular network over 4G, and one over the Wi-Fi on the campus. And what we do is that we just trace route to that server on the Google Cloud, and see how much latency each hop consume. And as we can see, like Starlink can outperform cellular network, but yet it cannot outperform the optical fiber connectivity. And this is mainly because they still haven't got into the inter-satellite links. So they still have implementing this pin pipe. So when we cross the Atlantic, which is the last hop, we still experience the same latency that the optical fiber experience. So we assume like when the inter-satellite links implement, we will not see that will not see that spike here. Another thing to notice is that on the second hop, which is mainly so the first hop is just from the router to the dish, as I said in the last architecture. So basically, this is the first hop, and the second hop from here to the satellite. We can see like there's a spike here, which is something around 30 millisecond or 35 millisecond, which is coming from the bin pipe architecture. So the message that we want to deliver here is that Starlink yet not overperforming optical connectivity, and this is mainly because of the limitation of the bin pipe architecture. So the second question we tried to answer is how that performs from one city to another, the performance of Starlink. So what we can see here is that it's another, this is a CDF figure. On the x-axis, we have a throughput in megabit per second. And then here we're presenting the Starlink performance in terms of downlink throughput for 3 different cities. The green one is Barcelona, the yellow one is London, and the white one is North Carolina. And here we present the throughput, downlink throughput CDF. So as we can see that the performance it changed significantly from one location to another. So for example, if we look at the median in North Carolina, we can see it's around 40 megabit per second, the median throughput. While, for example, in Barcelona, it's something around 100, 160, 170 megabit per second. So we think that might be due to some congestion, either on the satellites themselves or on the gateways that the end point of the pin pipe. So either
the same server.
Yes, this is going to the same
Where
server.
is the server?
It's this one was in Surrey,
Okay.
so it's in here.
Closer to the London and the Barcelona ones than the North Carolina ones.
Oh, let me. Yeah, no, yeah, it's not the same server. Sorry, this is not the same server. So we have a co-located server for each city. So we have one in Madrid for Barcelona, we have one in London for London, and we have one in North Virginia for North Carolina. So it's a different server. Yeah. So we think that might be due to the congestion, either because of the ground, like gateways or on the satellites. Yeah, so that's why we see. So for example, the service in Barcelona just came early this year in January 2022. However, it's in the United States for like a 1 year or more than that now. So we also tried to look at, okay, let's focus on a single location like the Starlink in London, and let's try to examine different congestion control and benchmark that against the Wi-Fi on campus. So we comparing Starlink using BBR, using Cubic and Vegas, Vino, and Reno, the traditional congestion control. And what we can observe here is that BBR is achieving the best for Starlink. So this is BBR for Starlink. This is Cubic for Starlink, and this is the rest for the other congestion control. So what we can see is that BBR is achieving the best in terms of congestion control if we focus only on Starlink. However, it's only achieving 50% of the available capacity that GSL link can provide. So how we measure that, the link capacity, we just did an iPerf session using UDP traffic on that pin pipe. And we saw that the maximum throughput we can get is something like UDP throughput, something like 300 megabits per second. Yet BBR is only achieving like 150, 145 megabits per second, which is much better than the others, but still only 50% of the capacity. Comparing that with the normal Wi-Fi, something around 90% of the link capacity. So what we're saying here is that, yeah, BBR is best, but still not fully utilizing the whole link capacity. And we think that might be due to the frequent handover that Starlink does, switching from one satellite to another satellite. So the question now, if you ask me how frequent that handover is happening, so this is something we're trying to understand now, to explore now, utilizing these 6 nodes. We're trying to identify the handover strategy that Starlink implements. Is it based on the nearest satellite, based on SNR, based on the capacity of the satellite, how many users they are serving, based on the beamforming? So all these trade-offs, we're trying to understand how this handover strategy is used over Starlink. So moving to the third one, we're trying to understand the effect of the weather. Here we're focusing on the data that we collect from the plugin, focusing more on the page transit time. So what is the page transit time? It's only the network-related component in the page load time. So we're talking about the HTTP request, HTTP reply, HTTP redirection, only the network layer related performance. And what we're comparing here is that we're only focusing on one city, on London, and we're trying to see the latency or the page transit time latency when we with a different weather category. So clear sky up to the moderate rain. And what we can see here is that the median value for the clear sky performance is something like 500 millisecond latency compared to something around 930 millisecond in a moderate range. So there's like almost twice increase in the latency in the rainy condition compared to the clear sky condition. Now, this measurement is kind of like application layer. So now we think if we try to measure something like throughput, like Mark mentioned, or like a packet loss, that might be more than twice or more than doubling that. For example, latency, for example, throughput might get dropped more than twice in a rainy day compared to the clear sky day, or packet loss, for example. So that might be high packet loss in a rainy day compared to a clear sky day. So overall, to summarize, so Starlink, as of now, performance is comparable with existing ISPs, but it still doesn't overperform optical fiber. We think that the inter-satellite link will boost the performance might be better than optical fiber. Starlink connectivity significantly changed from one location to another. It might be based on the capacity of the cells, might be based on the number of users served within these cells, and might be based also on how the gateways are distributed across the country. So how the gateways distributed for the United States compared to the UK. For example, we know in the UK, there's a 3 gateway location in the United Kingdom. We know that from the Ofcom filing, and they put the location of these. For the weather condition, the latency, network latency might be doubled in a rainy day compared to the clear sky day. So this is like an early stage study. We're still trying to investigate more, mainly from the active measurement platform that we're doing, trying to test other things, trying to see how the weather will affect other metrics, like as I said, latency throughput, trying to understand the handover strategy of Starlink. And thank you. That's conclude my talk.
Few in the chat, which I can ask online, unless there is somebody in the floor here. You have a question? Yeah.
So you're using latency to refer to the page load latency. Do you have per packet latencies as well? I mean, because page load latency could be affected by the per packet latency, or it could also be affected by just the throughput you're getting. And so it'd be nice to tease those two apart if you can.
Yeah, so now in that study, we don't have a packet latency, but we're planning to collect them from the nodes that's distributed over the different location. But yeah, this was only coming from the page load, the plugin extension.
I guess you do have the page transit time, which you defined. Did you show?
Yes,
Yeah,
but that's
yeah.
again coming from
the browser. Yeah, exactly. Yeah.
This is just a clarification question. So you mentioned that you were using this browser plugin.
Yes.
So how do you make sure that the client is using Starlink? Is it by checking the IP address and seeing like the ASN number?
Yes, we're taking the IP, but we are not storing the IP. We're taking the IP, query where that IP is, and then we know is it Starlink or is it different provider. We only store the ISP that use the Starlink. Yeah.
Okay, there's a couple of questions online. The first one is, do you have any information on where the Starlink POPs are for the different cities you're referring to? Are they all co-located against Google data centers that you're testing against?
So we know the ones in United Kingdom because they are filed by Ofcom. So we know there are 3 locations in United Kingdom. One of them is close to London. The other 2 is close to Scotland. But for the other ones, Barcelona and United US, we are not sure where are these But yeah, we can get these. These are public informations available. We can know them.
And you've done some trace routes which seem to point that they are Google.
Yeah.
Yeah. So you can't be absolutely certain because there may be other exits that you haven't measured. I hope that answers your question, John. Then there's another question here about whether there are any measures to ensure that congestion control results are consistent. There may be weather in one city at one point, not in another, depending on when the experiments took place. Also, time of day is a factor here.
Yeah, this is actually a very good question. So for congestion control, we did the measurement. All the measurement is the downtime in the city. So for example, in London, we did that after midnight, but that midnight will not be the midnight in the United States. So we did a separate experiment in the United States midnight. So we tried to make the experiment for congestion control and downtime, but if we haven't taken into account the weather condition at the measurement that we done. So we only did the measurement and the downtime only. But yeah, weather might affect as well while we collected this measurements.
Okay, thanks. Any final question from the floor or online? If not, we can move to the next talk. We actually have Dave Israel online now. So Dave Israel, are you able to hear us and are you able to share your screen and maybe start that? If connectivity is working, then what I'd suggest is we push the break back by 15 minutes because this is a half an hour slot talk. And so we'll have the break 15 minutes later than planned, but we'll have Dave's talk now. Dave, can you share your screen and is that working for you? He's certainly able to text on the chat. Oh, there you go. There you go. Excellent. Okay. Actually, yeah, Dave, you might be on mute or we can't hear you.
How about now?
Yes, perfect.
Yeah, I wasn't muted, but what was going on?
You're not on presentation mode, though we can see your actual slides.
All right. Yep. Okay. All right, here we go. How about now?
Yeah, I think there may be a slight lag, but
you see the title slide?
yes, we see the actual slide, I think, not the presentation mode. Okay. I saw you click on it.
Okay, perfect. So sorry about the rough start. I'm Dave Israel from the NASA Goddard Space Flight Center. I'm the architect of our Exploration and Space Communications Projects division, and it was out of our division. There was a study a few years ago that we integrated together and developed some different things that we coined the term LunaNet, and that's been getting adopted, and what I'm going to do today is to discuss. It's a high-level presentation about sort of what LunaNet is about. The beginning is just real quick what we're trying to do from the user perspective. But I'm going to try and go through this material sort of quickly in that I can field some questions that are perhaps more technical than what I get into in these charts, and I want to leave time for that. Okay. So just as like a background motivation that we had when we the big case that we're trying to make is that we've all gotten used to having mobile networks and connectivity combined with GPS systems in order to do our daily, say, your ops concept for your daily life here on Earth, and the case that we're trying to do for the moon and further exploration is to bring that ops concept and those ideas to that end user, that explorer, either human or robotic. So at the time when
Dave, can I interrupt you for a second? We still see your slides, and there's been a request on chat to put it on presentation mode. I guess it might be too small for some people. If you can.
So
If you have multiple screens, it might be that the
yeah,
other
yeah,
screen is.
this okay. Did that do better?
Yes, much better. Thanks.
Okay. Sorry, we don't. We're not allowed to use Zoom in NASA for some reason, so it's kind of hard to, to do. All right. Anyway, so the basic idea that we had, and that's what this cartoon with the astronaut was about, was where you can have a device, and basically it's integrating together the data flows that can be connected to anywhere on a larger network, and along with the position, navigation, and timing. And you know, on Earth we have weather warnings, but if you're exploring the moon, then it's more solar flare warnings. And to be able to have this network infrastructure that's able to provide all of those services to the end user. So I won't go through this narration, but we just kind of explain how you know, an astronaut can be out and about and get a solar flare warning. Anyhow, so the four services that we identified, and actually there were three in the beginning, and if you and I noticed the I guess the abstract for this talk kind of mentioned the three, and we've since changed it to be four services. So there's communications, and we'll talk about the specifics of the communications. One thing that is very different from our traditional space communications approach is that this is network-based communications, not just point-to-point links and saying things, you know, from that frame of reference. And then there's PNT, or position, navigation, and timing. So for Earth orbiting missions, over the last 20 years, everything's evolved to be really making the most of the GPS system. So there is, you know, some ability we believe, and it's going to be demonstrated soon, to use the Earth GPS and GNSS systems for PNT on and around the moon, but it's going to be limited precision and be not fulfill all the needs. So we need to have that service infrastructure. The detection service is, as I mentioned, for the moon. It'd be solar flare, solar energy particles. There is a time period where there can be some early detection, and then get a warning to an astronaut or to a system to take cover or to do what it needs to do. The detection service and sending those detection messages is one could argue perhaps it's less critical at the moon, because it's only you could get the warning there in a couple of seconds if it came from Earth. But we want to get this mindset and put it in place, because once we're going to Mars, then you know, having tens of minutes to get a warning out is too long. Plus, you want to do your detection more in situ to the local environment. And then the last service is the science and investigation. So this is something that's already done with deep space RF links and with the Mars relays, and that's using measurements of the signals themselves that we're using for communications and navigation purposes, but interpreting the fades in those signals or the ranging variations in order to be able to do science and determine things about you know, atmosphere in those places where there's atmosphere. And in the case of the moon, if we had a series of spacecraft with crosslinks, then we could use the intersatellite ranging to improve the models of the gravity model of the moon, for example. Okay, so when so this picture is the latest illustration, just trying to emphasize this point that was from the beginning with our LunaNet definition, is that the LunaNet idea, you can think of it as like the lunar internet or like the infrastructure that's sort of a framework, and it's not a specific description of an implementation, right? Like, so if somebody asked you, what is the internet, or when is the internet going to be finished, you know, it's hard to answer those types of questions, right? So it's really this architectural concept going in with this understanding that the full LunaNet is going to be built, managed, operated by a variety of entities, and the key is to have those standards and things like standards and governance and the like all in place to allow from a user on the moon to feel like it's one big network, like the internet appears as you know, a lot of ways one big network, when really we have all these entities working together. And we do believe that and it's really to achieve what we're trying to do. There's no single group or organization that's really going to be able to provide it all, and it's sort of better for everybody if we can build it up together. So that's NASA international partners, you know, any other commercial service providers, maybe there's other government agencies that are doing pieces, and we can all leverage each other's systems, you know, as appropriate with the right agreements and things. So what you see in this picture is there's these satellites in the top left are transmitting broadcast type signals that are the analogous to GPS type signals, but also have some broadcast data type information. There's a surface wireless system. We're looking at using like 5G or 3GPP mobile phone technology for the surface, and then you know, cross links between spacecraft, and then the trunk lines back to Earth, and closing those trunk lines back to Earth may be to ground stations, may also be to Earth orbiting satellites, and will likely be to both. There's really most of the answers to and/or things are and. It's not one or the other, and it will evolve over time as the requirements change and the technology changes. So let's see. So switching to I guess less the cartoons and more of the starting to get into the more technical look at this. Is so the way we've been discussing it, modeling it, is that there's this larger thing, the LunaNet, which you see in the middle there, and there's user segments on the moon and then on the Earth, and this picture and a lot of the things that you hear about so far talk about, like it really is people have in their mind that all the data coming from the moon is going back to the Earth, and everything coming from the Earth is going to say a single user at the moon, for example. But really what we're preparing for is to have things so that one user on the moon gets a LunaNet connection and is able to send data to something else on the moon. And then we start to get much more of the network effect. So you see that the interfaces between the users and the LunaNet, and we refer to the green part is made up of, you'll see in the next slide, the LunaNet service providers, or LNSPs, but there's an interface at the moon, and then so this with a lunar relay, so this could be an orbiting relay, or maybe something on the surface of the moon, like a equivalent of a cell phone tower, right? And then links straight back to Earth, DTE, and then there'll be the terrestrial interface. And the significance of these red lines is that these red lines are the things that we are working now to standardize. And there is a document, it's called the LunaNet Interoperability Specification, and we've publicly released 2 versions of it. There's a third version that we're working to get released I'd say it's either going to be the end of this week or the beginning of next week, where it will be published. And this is where we started it within NASA. Now we've been working on this document jointly with ESA. Folks have probably heard of the ESA Moonlight program, so we're working with them, and we're working to now bring in the other agencies, and in order to really get these standards in place so that we can achieve what I described earlier. So, so that previous figure is something that you'll see in that document, and then there's also this view where it's just trying to point out that we need these standard interfaces between a LunaNet service provider and the user missions. So that's you know, the first things people think of is like the RF links, the frequency band and modulation and encoding and all of those things. But we also are striving to have standard interfaces for some of the, you could think of it as service management or control plane traffic and things to be going between user missions and service providers, so that it's easier and much more feasible for user missions to get their service from multiple access points that may be developed by or operated by different service providers, and also you know, reuse of hardware and software and things, of course. And then there's also this interface between LunaNet service providers, and that's really from the user point of view, that's the stuff that happens behind the scenes, but it's to enable the idea of sort of roaming, like roaming services, like we have here on Earth, where I can go on travel to Europe and pull out my same cell phone, and I'm still paying my same cell phone provider back in the US, but when I turn on my phone, I'm able to get my phone service and everything from a local provider, and all those agreements and the paths that the data flows and everything is all transparent to me. So those are the types of things that we are working out in this interface between the LNSPs. So this is expanding that previous picture to just show two LunaNet service providers. So besides these interfaces that you saw between the user segments and the providers, so these red lines on the top left are to be the same services interfaces that you see, you know, with the LNSP-A, and of course this picture can be extended to multiple providers. But you see now there's the introduction of some cross links and other interfaces that would happen between providers. So I realized that, and I feel like I'm rushing through all of this, but that I mentioned the different entities and different people providing and operating things. One of the other key concepts is that not every relay or thing orbiting the moon, for example, is expected to provide every service, right? So we might have, like in that picture, there might be maybe there's some small satellites that really their main function is to be providing those GPS-like reference signals, and maybe they do low-rate data communications. But then there might be other orbiting relays that are focused much more on high-rate data services, etc. So this is in the draft, and I won't dive into all the details, but you see one of the important aspects is the frequency plan, and getting the coordination and the international agreements of what frequencies we would use for all the different types of links is of course important. So this is our frequency plan. Here it's one thing that's not shown on this picture yet are the use of optical links, which we fully expect and are developing and you know, planning optical links to be part of the future system, not just for their benefits of higher data rates and things like high rate trunk lines back to Earth, for example, or or to the benefit of reducing the size, weight, and power on user systems. But the moon has a very interesting property about where the far side of the moon is always shielded from the Earth and all of the radio transmissions from the Earth. So it's been a dream, I guess, since probably the beginning of radio astronomy, to put a radio telescope on the far side of the moon and have blocked out any noise coming from the Earth, and be able to see, make the measurements of radio astronomy measurements from the far side of the moon. So the idea of now polluting the shielded, they call it the shielded zone of the moon, with a bunch of RF signals for communications is an issue, and the use of laser communications or optical communications to move that data to and from the far side, of course, reduces those RF emissions on the far side. So I think that is, oh, I'm sorry. Wait, there's more. So I wanted to talk briefly about the PNT services. This is something that those systems that are implementing, like the discussion about the Starlink when I first joined in this morning. So the problem of providing the worldwide Earth internet access and high rate data communications on the Earth is focused on those data services, and we have GPS on the Earth. One of the things that we are making sure we don't leave out when we're pursuing our lunar applications is that there is no GPS. So there's a large effort to work out ways to the general rule, and any signal that's being used for communications, we want to be able to leverage it for position, navigation, and timing services. And any signal that's being used for PNT, it's a GPS-like signal, we also want to use it for some communications services. So similar to how the GPS signal has very low rate data on there, really related to the needs of the GPS signal functionality. But if we can increase the data rate some on those signals, then there's other types of traffic that we're looking to carry on those GPS-like signals. So there's a couple more slides. So the look at the GPS type signal around the moon and thoughts on that. This odd picture on the lower right is just showing measurements that have been done in the past, trying to model the gravity model of the moon, and there's still is a lot to be done to understand the gravity model of the moon, and also to work on the lunar frame and time reference that's happening as well. Okay, so now this is my summary slide. I was just trying to put it all on one slide. So again, you see the top right where we define the 4 services, and from the very first presentation, I had all these pictures where it was just these balls with different colors, because I was trying to get people not to immediately jump to this idea that it's all small sets, or it's all these huge Battlestar relays, or it's all things on the surface, or it's all ground stations, etc. It's sort of all of the above. So I didn't want to put any pictures of what the things would look like to kind of give people preconceived notions. And then the different color circles are there also to represent that they're not a homogeneous set of things, and they may also and will be operated and built by multiple entities. So I guess I hope I left some time for some questions, and there's some questions. If you if you haven't found any material about the LunaNet online, there is quite a bit out there. Like I said, there's the LunaNet interoperability specification, which is there. and soon to be updated. There was also the end of June a draft request for proposals, draft RFP that came out from NASA Goddard, our Near Space Network, where we are preparing to go out with a procurement for space communications and navigation service providers. And if you look at that draft RFP, you'll see that lunar services to and from the moon and around the moon are one important part of that procurement activity. And so there's more documents and things of what we're seeking with that draft RFP. And then when the final RFP comes out, then it'll be even more specific than what's out there now.
Thanks, Dave. There are a few questions online. Let me ask the first one before getting to the floor. I'm sure there are questions on the floor as well. So the first one is, will there be an international standards body allocating the spectrum? So who gets to decide which country or who gets what part of the spectrum space on the moon?
Yeah, so there is already there's this group called the SFCG. Maybe it's like Space Frequency Coordination Group. I think that's what it stands for. So the SFCG is the one that has all the recommendations and sort of governs the frequency usage, not just on Earth, but what we're doing elsewhere. So those frequencies that we have shown in our LunaNet interoperability spec were all based on recommendations and what came from the SFCG.
Okay, are there any questions on the floor?
So in the area of communications, how different are the requirements for communications around the moon than around Earth? I mean, could you just go and buy a couple of dozen Starlink satellites and chuck them around the moon and actually satisfy most of your requirements? Or is it actually just a fundamentally different problem?
There's some things that are the same. One thing that would be different for something like a Starlink design is the trunk link back to Earth is a whole lot farther to connect to Earth than the distance of any of the links that Starlink or LEO or MEO constellation around the Earth providing comm is planning to do. So certainly one could augment that, and that's where when we're going out with this request for proposals, we're looking for entities that think that they are planning to provide commercial services around the moon. So I would say that some of the requirements that we designed for our systems that are different than providing internet to the planet Earth is that a lot of our data is we want to get the data completely back, but we do it in we have different latency requirements. It's a sort of bulk data transfer of files of measurements and things. So that's something that I believe that we can take advantage of the fact that our users are not expecting or requiring full bandwidth end-to-end connectivity every time they have a connection, and that allows us to move the data in opportunistically in over any segment, any part of the path that is available, and also perhaps build up and be able to provide services with a fewer number of relay spacecraft, for example, because you don't need to have all the crosslinks and end-to-end connectivity that those types of challenges that lead to the mega constellations around the Earth. And then to provide that networking functionality over top of that particular situation, then that's one of the areas where you may have heard of the DTN, the Delayed Disruption Tolerant Networking bundle protocol comes in for our system. So we are looking towards our network. If you want to make sure that your data can get to anybody that's connected anywhere onto the LunaNet, then you would have your applications be transmitting and receiving bundles on the bundle protocol, as opposed to being like IP packet based applications, for example, or in the traditional space thing, just sort of like link layer connections.
Thanks. There's one more question that I'd like to ask from the online. Dave Tat is asking, is there going to be Wi-Fi on the moon?
So yes, I'm sure there will be. as soon as we land something, there probably will be. So so I expect there'll be Wi-Fi. You know, especially when whatever brings the humans to the surface will probably have Wi-Fi on board. We have it on board the International Space Station now. There is a upcoming demonstration of Nokia mobile phone service or usage on the lunar surface. So absolutely the idea that original cartoon with the astronaut with kind of like that tablet going around is that it would be for that astronaut, they would just be interacting with their well, it won't be a tablet in real life, I'm sure, but it'll be with their equivalent of the tablet, and some of the time maybe that thing is connected to through 5G like connection. Sometimes maybe it's straight to a relay. Maybe sometimes when they get back on board, it connects to the Wi-Fi system, inside the habitat. And the idea is that just like we don't have to keep track with our mobile phones, how the data is getting to and from the phones, as long as we can access what we want when we want it, then the network's working. And then to achieve that mindset, though, then it's really to get all of us working on it to stop thinking about all of the links as like that full end-to-end path. If you think about just the way people think with all the Earth systems, everybody just talks about like your connection to the network, right? We don't, you just want to connect to the network, and then there's this just assumption in the way we think about things that that once you connect to the network, then you know that then you can get to anybody else that's connected to the network, and it's only when maybe people are worrying about VPNs or security paths that they worry about the full kind of end-to-end connectivity and that path. But from a general user point of view, you show up with your laptop to a new conference room or a hotel or something, and you're just looking for that Wi-Fi connection and just connect to the network, and then everything else takes it.
I guess the most powerful thing of using something like Wi-Fi, or I think you also alluded to 5G, is that you can just take any user terminal from the Earth, and that sort of just works. But I wonder whether there's some additional complexity that comes with trying to put, say, a 5G stack on the moon, when you're already doing something different for trunking and things like that.
Yeah, so our goal is to really be able to reuse and leverage whatever is coming from Earth as much as possible. There are the challenges of radiation environments and lasting in the space environment and the like. But overall, it's better off if we're not doing things and starting completely from scratch and having it be so different than what we do on Earth.
Absolutely. Any other questions from the floor? I'd like to ask one final question, which is online. And this is about the GNSS service. So on Earth, we have a prime meridian, which is well defined. So where is 0, 0 on the moon? So how do you define the coordinate system there?
So I'm not the PNT expert, so I couldn't specifically answer that one. I did. I'm sure they have it defined, but one of my colleagues would have to answer that.
Thanks.
Sorry.
In which case, we are just at the time for the break, so we'll thank Dave for his talk. Offline, we've got tea and coffee here. And then for the online people, we'll come back in half an hour's time now. So what I might suggest to do for the online people is, while we are having this coffee break, if those of you who are able to put your cameras on, if you can put your cameras on, all of the ones who are offline, we had a nice photograph in front of a globe-like structure, which looked vaguely like a satellite constellation that we have, a sculpture we have in Surrey. But we'll try and take a screen photograph because organizers, the Institute for Advanced Studies, wants to see nice pictures of the community forming, which we seem to have quite a lot of interesting conversation going on online. So if you could maybe just turn on your cameras for a second, I'll take a few screenshots. That's okay, you can be in your PJs. As long as you've got your t-shirt on, that's fine, Peter.
And now for your in-flight entertainment, you know.
When you try and book it, it says, are you male or female? Because we need to know for the train. Oh. But then there is zero availability on the seat. So, like, perfectly zero availability. So I suspect it doesn't go. Or else it wouldn't be a good thing. I remember sometimes. Over there, and I'm looking at the wrong way. Nice thing. No, I've got the kind of the opposite, really. Trend is about one or two, and then it gets a little lazy. Thank you for that. Tom, thank you for the guitar. Put the seat. Yeah, well, I do the first class ticket.
You can come to all of our online meetings. You should come to like classes, right? And provide like a
background.
Might be
41 way School of Rock.
We can just rename it that.
Learn it for one day cost me about 50 pounds. Yes. That's the one. The package, £9.70.
So do you want me just to stay on the Zoom?
Yeah. So
Share screen on the
I'm
Zoom.
going to tell both of you at the same time, I guess. So basically what you're doing is share some. Yep. But without your screen,
seen if you follow sort of space news more in generally is the problem that we have around orbital debris. And that, of course, the more access that we have to reliable launch, the more access that we'll then have to then be able to do more services from space. But unfortunately, that translates into something called conjunctions. And conjunctions is where you have satellites that essentially enter these ellipsoidal shapes that are roughly 5 kilometers at its maximum between each other, where we would worry that those conjunctions turn into actual collisions, which can release then tens of thousands of perhaps objects. And this kind of plot that you can see here on the right here is examples of where we might have those sort of conjunctions. So these can happen for a lot of reasons. Most at the moment are through anti-satellite testing. Okay, so whether it is US, China, Russia shooting stuff down because they can, and that only escalates. Okay. So that's a problem that we can't necessarily solve today, and certainly in the 2 days that we have. But what we can do is sort of describe about what we might need to do in the future to actually make our systems safer, and to consider then what we need to actually put on our satellites as well to make ourselves more aware of this growing problem. So even if you took out then the sort of debris problem itself and just went, actually, this is perhaps a number of objects that we might have, period. How do we know where we're going? How do we manage conjunctions? And how do we do that? Got some statistics here on the sort of number of satellites that we have, certainly 40,000 sort of tracked satellites, with another 27,000 of those being sort of tracked debris. So these are not all cooperative targets, okay? These are ones that we may need to then have an estimation of through some sort of active radar or observation from the ground, but we might also want to do that optically or through radar sensors that we have actually up in space as well. Most systems are cooperative with their own constellation. Okay, and so if you're OneWeb, your OneWeb ones can talk to other OneWeb ones. Wonderful. How that talks to Starlinks, though, another question. Of course, we've talked about interoperability between systems already over this weekend, but there's been documented examples of where Starlinks and OneWeb have perhaps had conjunction warnings with each other, and one has waited for the other to communicate, and then they've waited a bit more because they wanted some more information from NORAD or the Joint Space Operations Center out of 13th Squadron, and then no one made a decision, and that could have gone really, really badly, and assumptions get made around these things, and we end up with over-reliance on other people's assumptions and other people's systems. Because broadly, everyone is pretty uncooperative. Unless there becomes a regulatory process that actually tells someone, thou shalt tell people where you are, why would you? And the reason why that is because companies obviously, certainly in the UK, have to meet their regulatory and insurance processes under the current treaties, the outer space treaties that we have, but we've got new laws that are currently being put through the House of Lords. The space industries bill is the one to watch out for, and I really do mean watch out, because there'll be things in there that will have impacts for you if you're going to be operators. But we want to understand what the limits are, and can we sort of do this and be a bit more proactive in this area before someone makes us do it. So in reality, I talked about the fact that we would use NORAD's sort of radar system to develop two-line elements, and you will have seen simulations galore from the work that's been done here in the computing departments, use these two-line element files, and they're slowly getting expired at the moment for a couple of reasons. One, this number of decimal places for your right ascension of your ascending node for the astrodynamicists out there, this is not enough, okay, for you to define a given orbit or something. And so there's the 3GP format, which is coming out, which will be better. But the problem about this is that this data is interpreted. When they release these, they are masked, i.e. they have a level of uncertainty or variance around them, which is not very good if you're trying to work out conjunctions between each other. Because if a satellite is roughly moving between 7 and 8 kilometers per second, well, that 5 kilometer bubble that you're trying not to intersect with anyone, well, that happens milliseconds, right? It would be good if you could get raw radar observations. That would be wonderful, because a real observation is something you can rely on. It's raw data, okay? It's not been manipulated, okay? That isn't available because it's usually done, again, by NORAD, which is primarily, again, a military system to detect missiles that have come in from other countries, okay? In the same way that we would have in the UK, our Farlingdale system, which is a big multispectral radar system, again, which is this missile early warning system. The fact that they point up, okay, and that we can actually get these 2 line elements is a bonus. But we shouldn't over-rely on these things. And really, that's what's happened in the last 20 years. Is we've been kind of over-reliant on these government services to help us solve some of these problems. And number one, they're not really fit for purpose. And number two, that's not what they were designed for anyway, and we shouldn't rely on them. 20 years ago, satellites had transponders on them to allow you to do ranging, an estimation of where things were. And that information is perhaps something that could be shared. When it comes then to getting your NORAD data, your 2 line elements here, it goes through processes. You don't know how it got there. It might have taken 10 radar observations, might have taken 1,000 radar observations. You don't know how much data has gone into generating those numbers because it's owned by the US military. And I'll get to data more generally later. When it comes to propagators as well, they kind of come in 2 flavors, sort of a low precision SGP4 propagator, which uses an empirical model, which roughly tells you where something is going to be in the future based on a given date. This is really great because number one, it's very, very fast. The con to that is that really the positional uncertainty is pretty poor. And that if you were to translate that into the future, well, 1 to 3 kilometers in low Earth orbit is your error. Okay? Not your covariance here or your estimated error. And usefully, anything past about 5 days is pointless. I mean, I just wouldn't bother using it. The data is not useful for this type of analysis. You also, though, have high precision orbit propagators as well. And those high precision orbit propagators are much higher in fidelity. They capture more of the physics. We know they are slower to run, but your positional uncertainty is much better. Okay. You can write your own versions of these if people wanted to for the astrodynamicists out there, provided you keep adding terms and you know what's happening with our sun and the solar activity. But each of these things kind of gives us this problem here that data isn't really accessible in the ways that we want it to be, and perhaps we've got over-reliances on data that isn't as good as we want it to be. So we've been doing some analysis on this, and I've got a few charts that I want to show you here today. The big one that we really want to look at is what we've been looking at for 2 line elements historically. So one of the things that one of my PhD students, Sam Lane, has been doing is we downloaded all of them. And when I mean all of them, I mean all of them, even the updated versions of any 2 line element set. And it kind of falls into 2 categories that you have. One, you have a series of objects that are really well tracked. And if we look at the age of a TLE, i.e. how old it is with respect to the current time, there are a lot of objects that are tracked really well. Well, the TLE ages, are, on the orders of hours. Wonderful, okay? There's this whole group of objects where the average TLE age is, even if you average it there, that's 100 days. i.e. actually, have we had an observation of that object within 100 days? Or is that 2 line element set good enough that the error with which it has still falls within that category? Okay, that should alarm people because it's about 50-50 between those 2 sets. If we were to translate that into conjunctions, well, just to give you an idea, the number of conjunction goes up. We've been observing things, but the more objects that have had, the more encounters that we've had have gone up. But the more conjunction warnings that we have to then deal with, i.e. operators actually should really do something about. They should even look at the probabilities involved. They should look at maneuvering. They need to talk with other people to understand what operationally they need to do, has gone up. And even in the last 6 months, Starlink has moved, well over 6,800 times. It's had to do that because of conjunctions with either its own satellites or other satellites. This is a problem. And it isn't going to get any better, I'm afraid. And some of these parts here are things that I've sort of been collecting, and I've got a big list of sort of mega constellations and systems that are going up at the moment. And if you look at the red boxes in here, oh, this one's going up purple. I think that might be the screen. Yes, the screen. There are people putting in FCC licenses for 13,000 objects, 114,000 objects, 350,000 objects, okay? I hope I want panic, okay? Because if we're gonna be then thinking of scale, this is the future that we have to look at, okay? And when Elon Musk says, yeah, there's loads of room, okay? We don't want to be rolling that dice that often, okay? And more importantly as well, we will have problems around just interoperability, period, just because of the number of services that are out there. And so Starlinks and OneWeb are currently in fights over spectrum usage at 12 gigahertz. This is only going to exacerbate the more that we sort of look at these things. So we've got interoperability problems, and we've got problems of scale as well, and whether or not these things are actually useful or not. So if I come back to observation, I kind of want to talk to you about then perhaps what we look at. Usually we look at a state vector within a satellite where we might have real observations. These are real, perhaps single measurements of a given satellite state. Let's say it's X, Y, Z in Cartesian coordinates, for instance. And it's got another satellite that's alongside it. But we've got, problem is we've got this area where we have uncertainty, where we haven't taken observations. This is a problem, okay? Because as we've just talked about before, the ways in which we used to predict these things, not so great. We've got this uncertainty and variance, where really what we need is we need more observation. We need to have better certainty of where things are. Because we want them to then really look like this. We want to have perhaps systems that can have measurements from lots of different places to allow us then to know actually where things are with enough fidelity that allows us to then perform conjunction analysis. So that when you put up your very expensive assets up there in space, that they can then provide then that useful service for you for the lifetime that you've designed it for, not having to dodge all these other objects, which I can assure you will reduce your satellite lifetime. So what should future observation look like? How do we translate this then to perhaps risk? If we add variance to some of the plots that I was showing you, well, the standard sort of age, when you look at the variance between them, actually starts to look even worse. Okay, so I'm looking at this plot here on the right-hand side, and forget sort of TL age is -1. When it's roughly about 0, its mean value is around 0, but its 1 sigma goes out to 1 day. So again, we've got some scheduling problems already that I can see in our system. Actually, we're relying on, everyone relies on. It's great for sort of setup. It's great for sort of beginning to do analysis on here. But all I can see in here is that there's an error bar associated to a lot of these things that we need to get a better handle on to find out how do we reduce that variance and bring down the total ones. All of our objects, we should be tracking all of them, okay? Because all of them, when they're traveling at these speeds, have the potential to produce massive amount of damage. So one of the things that I've been looking at is how you might then perhaps perform ranging between other systems. So in the same way that you would have a pinging system that we have between ships out on the sea. Does anyone know the system for that? You know what it's called? No, it's called AIS. So AIS sister ships, they ping out their location. Ping out location, unless you're a pirate, they turn that off, okay? But they ping it out because they know actually we need to know where these things are. We do the same thing for planes. We thought that was a good idea, called ADSB. ADSB is the system we use for planes so that they don't go missing, okay? So that we know where things are, so that we can arbitrate these things, prevent either collisions and schedule things actually where we need to schedule them. And I've been doing the same thing for ranging to figure out then what sort of spectrum, bandwidth, number of measurements, and signal to noise that I need to do to understand then where then I might then put each of these systems. And what I've got is I've got 2 plots here for you. The one on the left really sort of looks at different bandwidths to give you different amounts of certainty with regards to measurement. So if you were to receive a signal at, let's say, -5 dB, and it had a gigahertz worth of spectrum with 1 measurement point, well, actually, you can do pretty well. You know, you can get down to sort of meter level accuracies. Okay. Problem is when you start to add variance. Problem is when you realize your noise floors actually aren't that good. And that most people, when they're working out things, should really be looking at this 0 dBm mark here. Because that's really roughly what I've been working to. And 0 dBm gives you sort of errors here. And so even the worst one, if you used a 2 megahertz sort of bandwidth, and you took 3,000 sort of PRN coded measurements, well, then you're looking probably in the orders of tens of meters of knowledge, but with probably a couple of 100 meters worth of error. Those are still observations worth having, folks, because you can then decide to up your bandwidth. We have software radios now. We're all familiar perhaps with those. And if you're not, I'll ask someone in this room, probably, who will be able to tell you all about them. But those are systems that you can change. You can play with numbers of measurements. You can play with your estimators to then get you new things to give you a better idea around range. And one of the things that you can do is you can sense what is happening around you a lot better as well. And so if you are ranging by radio, you can have a system that works not just on an RSSI, really quite crude measurement, but you can actually have one then that is actually doing some autocorrelation as well with a sort of typical gold sort of coded phone or a Walsh coded phone, something that you would have on a typical mobile network that you could use on any of these other systems. And so the plot that we have on the left really shows you the step functions that you get for different bandwidths that are available already at different frequencies in either a navigation band, okay? There are lots of navigation bands that are out there that are used for planes, air traffic, ships. Those are protected ones. If the mobile operators start falling onto those, we'll be in trouble then. And I don't think they will. These are probably some of the protected ones. And of course, the higher up we go in frequency, then of course, the more spectrum allocation we can get, which means the more fidelity we can get. And so if you were to have 1 milliwatt of transmission coming out of, for instance, a system, you can decide how far it goes based on the frequency you're operating at, right? It's mainly what we've got, an inverse square law based on the actual frequency we operate. And if we did an analysis when we were looking at low Earth orbit satellites, and most of the time, even at low frequencies, even at 30 megahertz, okay, some really sort of HF frequency, you can detect lots of satellites in, on, and around you. And at VHF, yeah, you can get sort of tens. And the finer that you go, you realize you'll start to find the objects that start to matter to you because they are closest to you. They're the ones that you want to know more about. And so what we need then is we need a solution to allow you to range between satellites in an easy way, in a way that can be point to point. So exactly like an autonomous car doesn't send everything, to a base station server, do a calculation, go back. No, no, no. This needs to be some local optimum here. Because the problem is that when we look at what we've got a real problem in data. Data kind of comes in kind of three flavors in the way that I've categorized it: precision and accuracy, broadly, standardization, as well as sharing. TLEs, as we've talked about, these are not very accurate. Everyone shares them. Well, one group shares them really well, NORAD. This could go to 0 if things really kick off. But they are really good at sharing. GPS is super accurate. People don't share it. Not every satellite flies it. But with other systems, RF, Doppler, radar, these are things that actually, again, can give you a high level of precision. We just need to start sharing them more. And so what we've been building is an X-band transponder, or a system that goes up to high frequencies. This is an X-band transponder board, and we have a receiver board, and then we have a transponder here for performing ranging experiments between systems. This one is just CubeSat compliant because I've launched a lot of CubeSats, and so I will probably build about 4 of these and give them to people to fly, and then they can range between them at different frequencies. But this is one that I've been working on with my group of electronic engineers in the EEE department in the Space Center to actually go ahead and then perhaps start to test this. So hopefully you've kind of got an idea of really what is happening. There are about 12,000 Starlinks that are planned. There are credibly about another 24,000 in other mega constellations. I mean, credible ones, not those silly ones with 350,000 satellites. That's honestly bonkers. Okay. TLE age, and that is something you need to be paying attention to, because if it's an old TLE, you want to make sure that you can see if you can talk to the provider to get a better accurate estimate, so that that you don't have to do maneuvers, you don't have to change your operations. We need to think about how we data share and how that will then translate into regulatory as well as ethical processes, which unfortunately for companies, it will come out in the wash. there's a real sensitivity here, certainly for the commercial people in the room, that they may then be exposed. It may expose you because it's about the risk that perhaps you've been taking already that will somehow now be shown up by some policies. But if you actually had a ranging system to focus on a local optimum, then you can have that trade space. You can contribute to those systems. And I would, if I can, ask you all to consider when you're talking about networking, how you might include telemetry ranging and interoperability. So telemetry ranging is where you don't just do data, but you use that same signal as well to take time of flight measurements or measurements of signals to and from different places. Because if you can do that, then some of these problems can slowly go away, or we can at least have then a larger capacity actually up in low Earth orbit. And with that, I think I'm done.
Thanks a lot. I think we have time for possibly one question on the floor. Yeah.
So you mentioned telemetry ranging. It only works intra-constellation, right? Cross-constellation?
No. If you design it to be interoperable, then it will be interoperable. The question is what does that look like and what standards could you conform to? And so there are people that have been working on sort of ranging for 50, 60 years. These are quite old technologies, really. So either you have to give out your position and just start pinging it out, which is what most systems typically do. But if you didn't want to do that for privacy concerns or other concerns around the sensitivity of your assets, then you need to find another way to do that for you to identify yourself as whatever object you are, but for them to get an estimate on range.
Thanks. You're out of time. We can do this at the break. Sure. Let's thank Chris.
Thank you very much.
Next up is Geely Sun, who will be talking about their work in the Institute of Communication Systems. Oh, you're going to use this machine. Okay. Oh, well, that might not work so easily.
Oh, okay.
Yeah.
Maybe I can
just join in from.
Oh,
from here.
I'm sorry, that's me. Every time.
So how to connect?
Are you on Zoom?
No.
Oh,
I think I can use the other machine. Yeah?
Oh yeah, you can use that if you just use the USB stick. Yeah, that's probably the easiest.
Hello. Okay. Screen.
Maybe
share the desktop.
Maybe open.
Okay, first. Okay.
I think that's what most agencies are talking about now in the IDC. So, yeah. It's smart, right? Yeah, I reckon it's. I don't think we've formally met before. No. I think the analysis is done. We're not coming in from just say,
No right data. Variable quality.
Sweet.
Why was it variable?
Okay.
They don't want to know.
Hello, great. I'm not sure.
Oh, it's not sharing, it seems.
Okay.
I think we need to.
Yeah, from there. And see the. Okay.
Spending, see at the agency. Not enough.
Yeah, we need doing similar things. Yeah. Oh, it's hidden there. Yeah, I put it on top. Okay, that's better. Great, thanks very much. Hello. Can you hear me? Yes? Okay, great. Thank you very much. And in this presentation, I try to give you some of the update in IEEE, the working group for the future network for the 2030. Yeah, probably everybody heard about the future network, but the satellite became an important part of that progress. Not just IEEE, and also ETSI, European Space Institute, and also ITU, and 3GPP. They all try to look into the future because 5G, the standard has been finalized by 2020. By 2019, 3GPP, they consider to be this satellite really became a very important part of the future for the 2030. So in the IEEE, I get involved. I would thank many of my colleagues contribute to this part of the work. And this actually, I involved in the third edition, that's the 2022 edition. Okay. Okay, so the first I would have just a couple of slides and introduce about the Universe Center quickly, and look into the scope of IEEE satellite working group roadmap. Then I look into actually in the roadmap, the important reference to the 5G, 6G, the key performance indicator. So then I pick up one of the topic, quality of service. I personally contributed and getting involved more, give you some kind of idea, example, if you going to get involved with the AI routine, lots of other applications, you wish to get involved. And also the 5G QoS identifier, they have some parameter, we talk about since yesterday, today, how they work. And also the potential, the issue, the challenges, and the solution. And they give the time frame, and they'll suggest the way how we progress toward the 2030. Okay, that's quickly. Welcome to Surrey University. That's the picture. I think we are somewhere there. And this is the center for the Institute of Communication System. That's one of the center. The purpose built for the 5G, but after 7 years, we moved into the building. Now it became a 6G. Probably they changed already from 5G, 6G. So we call it 6G and 5G Innovation Center. We are part within the academic units. We call the Institute of Communication System, but actually we work with industry, lots of the support and collaboration lab, virtual lab is actually host the we call the 5G 6G Innovation Center. Yeah. So on the campus, you will see lots of the base station of 5G, 6G, 5G, 4G, and within the center we host the backbone, the core network of the 5G and developed to the 6G, the test bed. So the scope and most of the work we've been doing is related to the mobile communication and the satellite. For the mobile, from early stage, from 3G, we call it beyond the 3G, then we call 4G, then 5G. Now we move into look into the future, that's the 6G. So everybody start to talk about 6G, but the 5G start deployment. There's still lots of the work has been going on with the industry, how we deploy the 5G, continue to move and evolve to the 6G. And the satellite, and historically, it's the geostationary communication satellite, the mainstream, and for the fixed service, the video distribution, mobile broadband. Now today, lots of the work, probably more folks will be in low Earth orbit satellite. And also we get involved with some of the machine to machine type of the communication. That's you know, important part of 5G. When the 5G was standardized during the last 10 years. And also vehicle to vehicle communication consider was the one of the major area for the 5G. And also we look into we call the future internet architecture. That's looking into the IPv6, although very old, but still evolve. Now people look into, but today how you know we can get the benefit of IPv6. That's the group international network group, research, you know, for the future. And also ITU, they have a group just we call the Network 2030, particularly look into what's the issue. And also cloud, edge computing, security became very important. And also integration, particularly the satellite with the terrestrial network. That's the area we've been working on. Then we come to the scope. The working group look into, if you look at the document, it's available or published. This is the third edition. It's the first one look into the application and service. But currently, everybody said we got 5G already. We got enough bandwidth. The low latency, everything we can be enough. But why we need the 6G? What's the application? The loss argument and the discussion. Then people thought of one application. They called a kind of holograph type teleporting type of application, but considered to be one of the potential, like 3D two-way communication for the 3D virtual reality, you know, all that sort of application. Then they'll propose in the roadmap, particularly have they call the reference architecture, look into the backhaul and the direct access. You know, yesterday that was the presentation from Vodafone. That's interesting. Got a standard mobile phone directly talk to the satellite. That's important. But most of the currently like OneWeb and Starlink basically are kind of a backhaul. You know, you have one of the station. This station provide hotspots. People can use a Wi-Fi link to the hotspot, then send to satellite. The satellite IoT and edge computing, these are very important area identified by the working group, because many of the remote area monitoring and the service, you know, with the IoT will be useful, and also low latency requirement, maybe edge computing considered to be important. And a millimeter wave used for satellite network, machine learning, artificial intelligence. I'm not sure, you know, from my point of view, I think everybody can see that the AI is important in machine learning. So almost every part of the communication, including 5G, 6G, from physical layer, market layer, network, even application. That's security, network management. That's important, and also software-defined network and network function virtualization. That's important. That's the major part of the document. And the current version is 2020 and version 3. There is a continue evolve of all of this. So within the roadmap, they basically define how we evolve toward the future. So the first one is we call the 3 years near-term roadmap. That means with the system, they independently evolve to have those function, but provide interworking. That means satellite operator, you're just doing your job. Terrestrial network, you're doing your job. But we find somehow we can work together, link them together. That's the first of the steps. Actually, in the center, we had two of the major demonstration. One is with Avanti, with a geostationary satellite. That's to send the 4K video across the 5G network. And another one with Telesat, Canada. They have a kind of experimental satellite actually built by the SARI SSTL, and they did a kind of interconnection with the terminal, with our 5G testbed, and a link to their server. The second one is we call a separate virtualization. In the future, everything will be software driven. The hardware pretty standardized. Everything change in the future. Try to be in a software domain. So independently, 5G is one of the major parties like software-defined network and the virtualization, even the software-defined radio. Everything hardware try to be standardized and use software change to reconfigure. And that's in 5 years, both will be kind of introduce the virtualization, the concept. By the 10 years time frame, hopefully they have a kind of, we call a federation type of approach, and they can do in a similar way in the terrestrial and the satellite, the kind of seamless integration. So I pick up one of the topic, just quickly give you some flavor and idea how this working group is doing. And the quality service is important, mainly because the 5G, 6G, they define we call a key performance indicator like latency, throughput, and all these parameters I'm going to show you quickly. And from the quality service point of view and quality experience by the user, and performance is really important. Yesterday we discussed not just my terminal with the station. The latency they talk about the milliseconds and sub-millisecond. And actually the tolerance to the packet loss and tolerance to the delay, that's the parameter. Let's quick look into the reference to the 5G and latency. The current 5G standard, they say they have a 1 millisecond in terms of latency, and the per connection is 10 gigabit per second for the peak, and number of connection, the speed, and also another concept is slicing concept. It's basically the how you share the bandwidth resources. So there are two important parts. One is the network architecture, try to support that with SDN and FV, and also the new A interface. Yeah, that's the major development. This quick parameter, you can see the peak in 5G is 20 gigabit per second. 6G, they talk about 1 terabit per second. And expected data rate, and 6G is 1 gig, and 5G is 100 megabit per second. This is the parameter. You can just quickly look at it. Latency is 100 milliseconds. This is 100 microseconds. And reliability, jitter, and mobility. Mobility currently you can target the speed is for 5G 500 kilometer per hour. That means very high speed train you can be able to work with. But then you have we can 1,000 kilometer per hour. I'm not sure whether there are going to be a train at that speed, or maybe aircraft. Yeah, maybe possibility. So this and energy, that's the other things, and density of the network and the bandwidth, and from 1 gigahertz to 100 gigahertz. Potentially, you're going to in a high frequency band, V band, Q band, and D band. Yeah. And then they have defined we call the network architecture, looking to the bandwidth, that's the resources, and also the network resources, and some of the parameter, and also try to look into how this parameter affect the user experience. Yeah, many of the parameters really just the performance of network you can measure by the machine, but eventually people need to experience. And this is the 5 5G indicator, like a resource type, is we call the guaranteed bit rate. That's how much you can send in terms of speed. Delay critical, no delay critical. That's in terms of the speed. And also priority. Priority, you have a high priority media, maybe have currently you got a 7 level, maybe 8. And you can be in the MAC layer, IP layer, transport up to even the application layer, the priority. Different the application like a real-time video or download the web page, maybe you give a different priority to treat them differently. So a user get a better experience. And also the packet error rates, packet loss ratio, and also the average, the window and the maximum burst size or volume of data. So this is kind of an indicator actually specified by the 3GPP and also other standard, considered to be the indicator. But in the roadmap, they also have this. So the challenge is actually, the time frame to me is quite short. We already in 2022 now. Next year we're 2023. They consider to be, try to get this start implementation of by the industry, looking to from the 5G to 6G evolution, try to consider this is short term, looking to how to achieve this quality of service requirement. And then from 2024, 2025 is the kind of the function for the single network. That means individual operator, you should try to adopt this kind of the network architecture, try to implement this kind of software-defined system, virtualized system. And in this way, you can operate, make a quick configuration to meet the user requirement, can be done quickly. And in the long term, that's from 2026 to 2030. That means in the different operator, you need to cooperate together. You can have a seamless, easy integration if everybody adopt a similar standard. That's the challenge. Actually, the solution, they suggested some solution. And the solution, obviously, is currently looking to the future. But for the first one, mainly people talk about NTN, no terrestrial network and the satellite. That's by 3GPP, ITU, HC, all we work together, try to achieve this. One of the difficult part is, I think, is the new radio interface, because once you have a new radio interface, that means you have hardware implication. For example, you get a base station. If you're doing a software reconfiguration, virtualize the system, maybe that's fine. Can easily deploy in a way cross country. But if you want doing the hardware, it's a great challenge. But if this can be done, then hopefully individually, you need to look into in the satellite. But here in the satellite onboard, it basically just use existing satellite. Hopefully makes the work. Most of the work you can do on the Earth, on the ground. But by 2024 to 25, you look into the satellite payload. You maybe have some new issue, new technology, onboard processing, and also the advanced capability, particularly mention the low Earth orbit satellites. That's very important. GEO, and if we can solve the problem with LEO, GEO can be relatively easier. Yeah, and also consider it's optical communication for inter-satellite link. That's become a challenging issue. And remember, those inter-satellite link within the same constellation, maybe that's design already. And if you want to interlink between different type of constellation, maybe different type of the network, that's also a big challenge. And long term is 2026 to 2030. And of course, the software-defined radio, software-defined network. And also consider the routine adaptive orchestration. That means all different type of operator, hopefully they will be able to some kind of working together. That means just like today, if you pick up a phone from EE, you may be, be able to talk to the phone, connect the other constellation. So that's the very long term. But importantly, you have to meet the quality service requirement. Within the same network, we were designed, were tuned. You can, you know what's the target you can achieve. But once you send your packet across the network into others, and that's maybe not guaranteed. How are you going to do that? So I think that's is the very quick introduction about this. And also we have a workshop. I forgot to put there. Just if you search for we call the future IEEE workshop for the 6G system in the future, 6G system. Just very soon, I think 21, 17, 21 or something. I can send an email to the organizer. I can distribute for everyone. Right. Well, thank you very much. That's a little quick. Hopefully give you a good overview what the work has been going on with the satellite working group from the IEEE. Thank you.
Thank you, Jiri. Running a bit, but we have time for maybe one question while John gets set up and the team from VT also gets set up online. I was going to ask you, if there was no other question, I was going to ask you about the importance of LEO versus GEO. Get set up, John, and then we can, LEO versus GEO for the IEEE satellite working group, because I guess most of the
GEO, remember GEO is still very important because most of our today operational communication satellites is GEO. Remember that they will be continuing important, and also GEO also evolve continuously. They have probably people heard about the high throughput satellite. They have a spot beam. This spot beam provide a very high speed, high throughput. So that's a very still continuously important. But LEO introduced an additional dimension and for the global coverage.
Yeah. Okay, we are running about 15 minutes late, I think, but we now have the final lightning talk from Virginia Tech showcasing their capabilities for small satellites.
Good morning, good afternoon, everyone. I'm Joseph, and I'll be speaking on behalf of NetSat, basically the Virginia Tech side for this network testbed. Since we did an overview of the software and touched a little bit on the hardware, we'll be talking about how Virginia Tech can enhance this testbed and what applications that Virginia Tech may continue as a result of this testbed. As I said, this will be an overview for those who just came today, and maybe a little bit of review for those who came yesterday as well. Our motivation essentially is to uncover what is the industry standard for this type of technology, discover any methods on how satellites talk to each other, and then overall develop APIs to serve for users, whoever wanted to use this testbed. Some applications that we're looking into is, of course, the routing and simulation and the ground station satellite protocols. We also want to look into 5G and 6G protocols and cybersecurity measures as well. To bring this with the software architecture, as we discussed, it's built upon an Mininet and the hardware integration, so a top-down system with this in mind, it allows users to configure the testbed to their own needs and hopefully create new applications and solve any research opportunities.
Hello, my name is Richard Gibbons. I'm a graduate research assistant at the National Security Institute at Space and PT. I'm just going to be presenting on the current status of the hardware. So if you were here yesterday, it's also going to be a review. But to cover what we currently have set up for our network satellite testbed, where pretty much we have in gray representing the network simulation, which then feeds into a network switch, which then feeds into actual hardware. So going from the left, we have our basically a Raspberry Pi with a USERP software-defined radio acting as a satellite in our communication. And then on the left, we have another Raspberry Pi with a software-defined radio acting as a ground station. So these are pieces of hardware that are going to act as this satellite ground link for testing and emulating communications. And so in the middle, we use a digital attenuator to actually emulate how that signal propagates from either satellite through the upper atmosphere down to a ground station. And so all these pieces of hardware are getting fed data through an Ethernet switch coming from the simulation software. And so, like I said before, we use a programmable attenuator. It's just a device with the capability to change attenuation based on where the satellites are located, maybe even space weather patterns, etc. And so we use Raspberry Pis as the single board computer to actually emulate the processing that's going on inside or on a given spacecraft. And so, and this image in the lower right-hand corner that you see here is actually our GNU radio setup, where we just did a basic send and receive of one packet of data going from a satellite to a ground station in the hardware testbed. And so you can see the spectrum of that signal actually propagating through the attenuator. And so our next steps for this are going to be to automate this data communication and actually integrate it with the MiniNet and simulation constellation that the University of Surrey created, and to scale this up towards 5G communication protocols. And so here we have a basic visualization of what's going on with the simulation of the hardware. So in this scenario, we just have 2 satellites and 2 ground stations, one ground station at Virginia Tech, another at the University of Surrey. And moving forward, you'll actually begin to see that link form. So it's our plan that with this visualization, we actually take the routing tables from the simulation that the University of Surrey created, and can actually visualize how these links are generated. And then we can scale this up for more complicated satellite networks like OneWeb or Starlink. And then, and then I'll hand it off to Dr. Black.
Unmute. Okay, there. Can you guys hear me? Great. So yes, thank you guys for that. And I think that we've kind of been talking about some of this, but our vision is the hardware in the loop testbed, and being able to expand and network multiple testbeds in, such that ultimately we would have external users be able to bring in their hardware, right, and then really do this multi-constellation heterogeneous orbital regimes, and a bunch of different routing protocols, algorithms, communications, right, 5G, all of that, and have all of that laced in, and then be coexisting, right, and do all of the coexistence studies of the multiple networks and the multiple architectures, all networked together in this fashion. And the reason that there's a primary and secondary servers, right, would be the links between Virginia Tech and Surrey, right, to begin with, and then we would add this in for the rest of the community. Okay, next slide. And on our end, there's a group that you haven't heard from. They're the Wireless VT group, CoreNet, very similar to what Geely just presented on this side, but they basically do all of the wireless and the 5G, 6G research on our end, and so just showing that our goal is to connect those together to kind of have the hardware side, the satellite dynamics, and then all of the wireless links emulated together in the hardware in the loop. Okay, next slide. And then other studies that we're going to do, there's also a statewide initiative in Virginia called the Commonwealth Cyber Initiative, which is multiple universities around the state that are all working together. They also have test beds. They have an XG test bed. They have an autonomy and cyber test bed. And there's multiple different ways of applying cyber effects into the networks, testing network resiliency, et cetera. So these are some of what we're planning on doing, again, in conjunction with CCI, but there are, again, a number of other studies that we can support. Okay, next slide. And then yet another test bed here is what we're calling space drones. And so this is a spacecraft swarming ground-based test bed that uses, currently it uses multi-rotors and in drones, but it does this hardware in the loop autonomous space simulation where we're emulating, we're simulating the environment in software. We use the Unreal Engine to build up some of the scenarios. And then this YouTube link here, which we'll maybe show you later, has a truss assembly where we're projecting it onto a 10-meter curved screen. We have real trusses and we have simulated trusses in Unreal Engine, and then are detecting, picking up the truss and moving it around. And so in a fashion where you would have a lot of small autonomous agents that are doing a large construction project, right, on the moon or in orbit, for example. This is how we would build up both the data, all of the autonomy, which is a set of, there's a whole bunch of studies that are, but cognitive neural nets, right, that run on board, and then actually simulate the overall construction project, and how much data you need, how much autonomy, how much onboard processing, and all of those different components. And we actually have this in, again, this kind of theater facility where we're able to do lots of trials, lots of tests of it in lots of different scenarios, but again, applying all of these to the hardware. Okay, next slide. So I think we've probably hit on most of these APIs, disruption tolerant networks. We've been talking about laser communications here a lot offline. We didn't mention that here, but we have an ability to bring that in as well. Okay. Anything else we wanted to say on this, Sam, at all?
Oh, no, just that this is kind of enhancing some ideas we have to enhance the hardware and to allow other technologies to be incorporated. You know, we've discussed, we have Raspberry Pis talking to USRPs, but we hope to incorporate custom hardware in the loop of everything, and then managing everything through like Ethernet ports that can basically function as simulating the like real links that would happen between spacecraft to spacecraft or spacecraft to ground station in the air. So that's incorporating some tools that already exist like SatCat5 for that management, or maybe getting an Iridium Edge Pro module and communicating with that with our hardware. Also, White Rabbit is something based out of CERN, which deals with Ethernet communication management, and we could maybe leverage this for PNT studies. And we know this is also an objective of LunaNet, so maybe a way that we collaborate and incorporate our test bed into LunaNet objectives. So. And
one more that we did mention before is we have a network of ground stations across the Commonwealth of Virginia, including some of the very large antennas and dishes at Wallops Island. So we have plans for looping those in to the overall network test beds as well, and actually running some of those through our fixed satellite services, both in Blacksburg and around the Commonwealth. Okay, great, thank you.
Maybe time for one quick question from the floor or from online, if there are. one now? No? Okay, but you had a question. Sorry. Oh, there's
Oh, yeah, there's the YouTube video.
the YouTube link. John Earl says it's not available. So maybe
Okay.
Sam and Co, if you could
Yeah, we'll post that.
post that on the Zoom chat, the right YouTube link. That's probably helpful. Okay, let's thank the Virginia Tech team. And John, do you want to introduce Ella, who's
Yes.
the next speaker?
Okay, I think they stopped sharing. So Dr. Atkins, if you can share your slides.
Can you hear me okay?
Yes, we can.
Okay, I will share my whole screen and then start my slideshow and then duplicate it. All right, can you see it okay?
Yes, ma'am. I will do a quick intro here. Dr. Atkins is the new, or as of the next month, will be the new department head at the Kevin T. Crofton Department of Aerospace and Ocean Engineering at Virginia Tech. She is currently a professor of aerospace engineering at the University of Michigan, where she directs the Autonomous Aerospace Systems Lab, and until 2020 served as the associate director for the university's robotics initiative. And she's going to be talking about space robotics applications and the needs for networking and distributed data collection. So thank you for being here.
So I apologize in advance. The talk evolved after I needed to send the title and the abstract in. So you're going to be stuck with what I have to say over the next few minutes. I also haven't started my new job. Just a little background about me. At MIT as an undergrad and master's student, and then as an assistant professor at the University of Maryland, my research focused on space robotics, in particular doing neutral buoyancy simulation of three-dimensional robot, free-flying robot for applications for things like docking and inspection of space structures, et cetera. And so I'm going to bring some of those kind of old school insights. I haven't done neutral buoyancy work since 2006 into this presentation because I think they're still relevant, even though the year is 2022. One of the things I'm also going to point out is the things that we were talking about back when I was a young undergraduate in the 1980s are still at best demonstration missions. So space technology development is especially for robotics has been extremely slow, as we all know. And so we really, I guess, the kind of underlying theme of this presentation is we need this kind of kickstart for space robotics missions and our level of ambition with them that we've kind of gotten from a company like SpaceX, where we used to think that it would be really long and slow to do some of the development that they've done over the past few years. And I'm pointing them out as a company just because I think it's unquestionable that they have had some disruptive effects, and we need to have that for space robotics as well. So the outline, I have three different parts of this talk. The first part were some slides that John Black shared with me. So I'm going to go through them very quickly because I think the actual folks from Virginia Tech that have already presented have done a better job than I'll do as a, let's say, a newbie coming to Virginia Tech trying to learn about the activities of space at VT, but I'll still do a little bit of presentation there. The next thing I'm going to talk about is just a couple of my kind of thoughts and insights, high level, not down in the technical details about space communications, not only for space missions, but Earth use cases, because one of the things that we've seen over all the decades that we've done anything in space is that the public needs to have buy-in to these missions for them to actually get the funding that they need to be successful. And for that, you need the public to be excited about the space-based assets. So the Earth use cases are not just because, for example, I want my internet on my farm. They're also because those types of use cases can be argued as real value for your tax dollars, which allow the missions to be more successful in terms of funding and level of ambition. And then I'll talk about the space robotics. So space at VT, I kind of feel like John should be presenting these slides instead of me, but I'm pretty excited to learn about it and to join the group. as a minor player, given that my major role is going to be as department head, but to try to get back myself into some of the space robotics missions to support space at VT as well. So the idea of the group is very cross-cutting, many departments, where in science, we want to have research that leads to understanding of the science. You see here pictured solar science. You see Earth with all of the wonderful things that we do, not only on the Earth, but above the Earth to do science, exploration, transportation, many things. And then also to help the students really go from being in K through 12 programs where maybe they've seen a lot of PR about space and how great it is, and that's why they choose aerospace engineering, in particular space, for their undergraduate studies, but they really don't know what they need to learn and how they need to apply it. So the education and training is not only for the engineers, but also for those who choose management, political, and other careers, so that they can do the best job of working with future space scientists, engineers, computer scientists, and others that all need to form the best teams to make the disruptive space robotics and space exploration and space communication advances that we expect in the future. So the idea of space at VT is to be bigger than one department's group and to engage everybody, whether it's industry, government, people at the university, alums, so that there's just more awareness, more collaboration, going after center level proposals. That's the department head and me speaking, and other initiatives to make it a bigger, better thing. So this is a picture of the group. I guess it's a recent picture showing that there really are a lot of faculty and students with a lot of different expertise. So there's electrical, computer, aerospace, science, looking at anything from theoretical modeling to how do we do better sensing from both ground and flight platforms on Earth that can better inform what happens in space and on planetary surfaces. So here's some of the projects that I think John and others will talk about if they have not already as part of the workshop. I heard him just now talking about the drones in the bottom right. And so it's pretty exciting to be able to actually have the multi-vehicle, three-dimensional flight resources that are really just giving us a picture of what these operations would look like in space. Yes, on Earth, I have a whole slide on this later, but it's there are different space simulation environments, and each of them has its pros and cons, but certainly the drone is just about the lowest cost, most flexible way to get three-dimensional motion of one or multiple vehicles to do many of the proximity operations tasks. And Virginia Tech is well positioned to do a lot of important research in that area, whether with free flight, with manipulation, heterogeneous combinations with flying robots, humans, and manipulation along with space structure mock-ups, which is something that I've been working on at Michigan over the past couple of years, because there's a lot of challenging projects in all of them. I think that one of the things I'm going to remind this group of is that, at least in the United States, which I think is a little bit unique, there's a big emphasis budget-wise on human or manned spaceflight. Having crews aboard vehicles that are traveling either to new destinations or to space stations. So I think that that's something that is important to think about in the activities at Space at VT also. And so hopefully I can bring a little bit of that myself to the future group. So in terms of space sensing and guidance, there's a lot of stuff going on here. Understanding how to take data and process it and optimize the missions all the way from the top end to observation targets. How do you process the data? And also how do you manage the communication, which I know is a big topic of this work. I'm really a big fan of this kind of VR adaptive configurability idea. And for me, this notion involves people both on Earth in kind of revolutionary new mission control stations, as opposed to the old school 1960s, sit in front of a green screen monitor as a big group and look at one function at a time. but also what's happening in situ, where there's people maybe in spacesuits if they're doing EVA as well as inside vehicles. Data processing is such a huge thing, and certainly astronomers and other astrophysicists and others have been atmospheric scientists looking at space-based data collected for a long time. And wow, who hasn't just been really inspired by the recent James Webb Telescope images that are coming back? So there's a lot of stuff that we are getting from science that's just so exciting. And when we really begin to lift the data fusion capabilities that we're seeing for things like self-driving cars on Earth into space, it opens up a whole new realm of opportunities for space robotic as well as space science missions in the future. All right, so here I am, somebody who doesn't do space communications for research, talking about space communications. So hold your breath and don't be too critical, but jump in if I say something wrong right now, just to make sure that I don't kind of overstep my bounds of knowledge. So here's my understanding from my little world of traditional space communications. So first of all, we have a lot of ground-based assets around the whole world, including Deep Space Network, but I separate them because a lot of the communication stations are for CubeSats and Earth-based orbiters that are not specifically looking beyond the Earth orbit. So no matter what we launch, we need to have communication. It doesn't make any sense to launch a CubeSat if it can't tell us what it's doing, because the human doesn't care. So if we have connections between space assets and the internet, then if they are low cost, if they're easy to replace, then that's great. But anytime we have something on the ground that is big and fixed with a big dish or antenna, it can't move. So as the orbiters move around, they have to constantly be transitioning between assets and so on. There is incomplete coverage, costly to deploy in remote areas. I'm thinking Antarctica and the like. And there's limited redundancy, meaning that if we have big monolithic ground stations, when they fail, then we have blackout periods for the orbiting assets, which are going to orbit anyway. We have traditionally had geostationary, geosynchronous assets. Really, I think what's relevant today is not that I'm going to tell you something new about these well-established, predictable assets, because they have been tremendously useful for the past 50 to 60 years. But I think the big deal right now is that we think they're not good enough because we all want Zoom and other things to do, and they don't work well for Zoom. There's just too much delay if you have a two-way conversation because of the orbital altitude and time of light travel. So we want something better, but I want to point out an advantage, which for me is just a scary thing about where we've gone. There are not so many of the geostationary, geosynchronous assets compared to what we're thinking about when we have the lower Earth orbit assets that give us lower delays. And I'm afraid of that because we're going to have a lot of space junk. That's on the next slide. So Deep Space Network solves a really hard problem and has let us communicate with orbiters that are far away. But we know the disadvantages. I mean, you really have to pay a lot of attention to optimizing the data that's being sent, compressing it, because there's just a limited bandwidth for that type of resource, because everything has to use it that's beyond Earth orbit. So here you're seeing this strange picture in the upper right. Don't worry, I don't plan to launch my truck into space to crash into the Tesla that's already there. But the reason that I'm showing that is that I actually have a farm near Virginia Tech that has not had internet for the past, I don't know, 35 years that I've cared. And now it does. And the only reason that it has internet is because of Starlink. So I am a big fan of Starlink because I'm talking to you right now through Starlink satellites. It's the only way that I could without actually going to a larger town. So this is one of those big wins for me personally, and for a lot of people who might otherwise be skeptical of space-based communication as the next generation internet for those who can't otherwise have it. I think we forget when we're in really well-covered areas that have underground or whatever fiber, that there are a lot of people that can't have that option. And so that's really a great benefit for these next generation space communication systems. And Starlink isn't the only one. So the advantages, boy, they're huge, right? You get low latency, high bandwidth, high level of redundancy, and you can get that data anywhere across the world. Any of you that have been out on a ship for a long time, and I have just for a couple weeks here and there, but you realize that that wasn't a thing, right? You can't put cell towers or fiber connected to boats that are far away from the coastline. So this same networking can give any sort of mobile asset this type of coverage, which is awesome. I really worry about these disadvantages because I think with these big step changes in advantages, we're going to really see a political problem as well. And I'm not well qualified to fight that fight, but I think it's going to happen. We can't avoid it. What happens when 20 different companies from 10 different countries launch Starlink equivalents? Well, you get a whole lot of spacecraft up there, and you guys have thought about this, but what happens? Well, the spectrum becomes almost impossible to manage. In fact, I'll tell you, because I have this Starlink antenna and I do love it. Starlink sent me a political lobbying email saying, contact your Congress people to tell them how great Starlink is, because they're currently fighting with Dish Network for spectrum access. I guess Dish is suing them because they're using the same frequency band. So I don't know where that's going to go, but politics and law are going to factor prominently into these new communication networks. Also, the physical resources themselves are going to factor prominently into our maps of space junk and debris, because they're not just going to deorbit immediately when they become dysfunctional, because they have a certain lifetime. For Moon and Mars, I guess I would say some of these orbiting networks can help. It's not just on the ground. The question is, do any of them look up toward these other locations rather than down? And that's really, I think, a challenging communication question. I mean, I've seen it personally in a lot of my unmanned aircraft work. Because I would love to use 5G everywhere that we fly unmanned aircraft, because the need for communication is greatest in populated areas where 5G is available, since detect and avoid and coordination of routes is a big deal in those areas, whereas flying over an unpopulated area, it's still very unlikely that you're going to get into trouble with colliding with another aircraft. So that doesn't mean I'm doing anything with policy in this discussion. It just means that I understand that that's a problem. Many years ago, the cell companies decided not to point their assets up, that they could make more money by only providing a very low altitude cone of coverage, because nobody was listening when they pointed their receivers up toward the sky to communicate, which means that you can't actually use the 5G network until that changes, which hopefully will happen next generation as we talk about advanced air mobility, so that we get that kind of coverage, not just go in flight, that we want to have everywhere for every new vehicle that has high bandwidth data communication needs. Well, I think the same could happen in space. And that's why I bring up that analogy, not to bring you all into unmanned aircraft, but to say, if we're building this giant network, which is a space-based equivalent of 4G, 5G, and beyond on cell towers, then we are asking the same question now. Do we point them up? And if so, why? And what will be the monetary business case for that? Or do we keep them all pointed down to satisfy Earth-based users, but then not offer them this dual use of actually communicating with higher altitude Earth orbiters and beyond Earth, Moon, Mars, and beyond assets as part of the network? I think that's about all that I wanted to say. I put another picture on the right as kind of a counterpart to my old 1977 Dodge truck with its new Starlink receiver antenna, but also to point out that we are doing some interesting things. Capstone, the NASA orbiter for the moon, is up right now. Lost communication briefly, but I understand it's back, testing a novel lunar orbit. And it's pretty exciting to see that we're going to get some coverage for the moon that is kind of decent, as opposed to just a few passes here and there per day for any landing asset. I wish I was in the room. I'm sorry I'm not there, but I'm on Zoom, because it's very hard for me to see like what you're all saying. Are you shaking your head and pounding your fists because this is high level and maybe wrong, or so I look forward to your feedback. Hopefully we'll have a little time for question and answers. I look forward to maybe meeting a lot of you soon. So now, breathing deeply and talking about space robotics, which is something that I haven't done a lot of at Michigan because aircraft was a better opportunity for me there, as well as even some cars, because in Michigan, you got to do cars. But there's a lot of that work that can apply to space robotics. And so here's kind of my broad view of what space robotics is and how it might go in the future. So for me, a spacecraft is a free-flying robot. Why is that? Well, if you look at something like spheres or other robots that have been developed as free flyers in space, they don't do a lot different than a satellite or a spacecraft. They have a processor, they have GNC, guidance, navigation, and control. They have the ability to communicate, collect, and process data. And if they're somewhat autonomous, then they don't need immediate supervision, which is where we've gone for many years with the spacecraft that have mission control connections. But we don't want someone sitting there 24/7 looking at very boring status messages coming down from a very well-established orbiter. That's kind of interesting, because then you can begin to draw analogy between what we call autonomous vehicles, which in Michigan is cars. And I've fought that for years, and it's just the way it's going to be in Michigan. But when you actually say autonomous vehicle, it's much more general than cars, and it includes space robots. Second, if we have ground-based or underwater landers or mobile robots, so where am I going with that? Well, the moon and Mars are ground, as are asteroids. And Europa it's not really water by chemistry, but we think of it as water because it's a fluid. Then a lot of the robotic technologies that we build for Earth-based environments can be thought of as analogous, even though we have additional challenges in the space missions. So now space robotics is drawing directly from ground-based and underwater robotics and trying to translate those results, which we've done for decades in limited ways, to the extraterrestrial environments that are the closest match for what we can find on Earth. The third category, which we've also done for decades, is in-space docking, manipulation, and free-flying robot operations. And so these are the things where we have either maybe a larger spacecraft or a space station or space shuttle, some kind of vehicle that needs something done to it, or at least an inspection. And now we have other vehicles that are coming up to it. So for example, every time a launch vehicle delivers astronauts to the space station or carries them away, or supplies, it has to dock and undock. And that's actually a pretty, as you know, an interesting guidance, navigation, and control problem, because you also have to deal with orbit dynamics and the whole trajectory of having very low friction and causing lots of vibration to the relatively flexible space structures when you hit the docking. We've done each of those things solo a lot for the docking and manipulation, because we've had large manipulators on manned space station and shuttle type vehicles for a long time. The free-flying robots have been less plentiful. I think there's been a lot of hesitation because there's worry about them colliding and damaging the structures, and maybe some thoughts that they had limited use. But we know that there's many uses, and especially as we have more servicing applications and clusters of satellites, which we're seeing, like with John's work with multiple drones working cooperatively to collect data. I want to point out here that combinations are going to be really useful. So if we have multiple free flying robots, there's nothing to think that they can't manipulate or dock with each other or larger systems, as well as flying freely. They also could accompany people. So that last point is on human robot collaboration, which is a generalization of HRI, because it's not just about the human and the robot communicating in a very kind of clean academic way. This is a human and a robot in a very hostile environment, which is true of any extraterrestrial place, and trying to get the job done. So whether it's IVA, intra-vehicle activity, which means that you're in a habitat and a person will typically not wear a spacesuit, or whether we're on EVA, extravehicular activity, and the human and the robots are outside the spacecraft or lander or habitat if they're on the moon or Mars, then there's a lot to do in robotics. And so all of the work that we've been doing, whether it's in self-driving cars where we want the person to actually interact with it, or self-flying planes where we want a pilot or an operator on the ground to still supervise and manage the anomalies and contingency plans when they are developed because things fail or there's bad interactions or bad environmental conditions, we still have this notion that we want humans there. Now, I'm an autonomy person, so I've typically been in arguments on the side of, well, we don't really need the human there, at least not in a few years, because we have the ability to collect data, to build rules, to use machine learning and guidance navigation control that can be provably correct to get to the point where the vehicles are going to be sufficiently capable without human supervision. We're not quite there yet, but there's a difference. You know, my colleague Nadine Sarter, who focuses on human machine systems and cognitive engineering, has a very eloquent hour-long, so I won't do it here, presentation on trust and calibration of trust. Calibration of trust is really hard, especially for space systems, because there are such limited opportunities to truly collect data from human-robot collaboration tests. And so we continue to have difficulty in calibrating trust properly. Calibration means that you neither overtrust nor undertrust the automation or autonomy in a system. And so that's something that we really, really have to get right when we send more ambitious, disruptive human robot systems into space to do exploration and science. But, you know, we're going to get there. If we're going to have these manned missions, we have to figure out edge computing, data management, perception, physical task completion, autonomy for the robots that assists the astronauts without diverting the astronauts from themselves being productive in space. That's how we optimize overall productivity. All right, so now a little bit back to Earth. And this picture on the right is a blast from my past. I was at the University of Maryland where there was a neutral buoyancy tank. The robot on the left here is SCAMP, the supplemental camera platform that was truly neutrally buoyant in 6 degrees of freedom, free-flying robot where flying was done underwater. And this was Ranger, that was designed to be a prototype of something that could have robotically repaired the Hubble Space Telescope back in the day, which was 1990s, early 2000s. And so these vehicles were collaborating in this picture by SCAMP providing camera views of the manipulation that was almost impossible to do without the supplemental camera view, which showed an early version of collaborative robotics. Now, why do I show this? Well, first of all, just to advertise something I did over about 20 years ago. But second of all, to point out that we have real challenges, not only in developing and testing hardware systems with the thermal, radiation, vacuum testing environments that are supplemental beyond what you would do with any sort of Earth-based system, but also for robots, we really have to work hard to have the three-dimensional, true 6 degree of freedom, 3 positions, 3 attitude, zero-G emulation environments on Earth that get us close to what we're going to see in space for robot GNC, guidance, navigation, and control. And we can do a lot of simulations, but as everybody knows, it's hard to really kind of tease out the things that aren't perfect in your simulations, because simulations are in fact doomed to succeed if you're not careful and you don't get the models just right. So I'm just listing what we've done over the years here. This doesn't have anything novel in it because we've done each and everything. Early on, we designed air bearing tables that were kind of like hockey rinks, and we put little robots on them to give us 2-dimensional constant altitude, I guess I'll say, motion environments with extremely low friction. That gave us the frictionless vacuum-like environment, but we didn't get 3D. We only had XY position and heading as degrees of freedom. We obviously have flown for a long time in aircraft that could fly parabolic trajectories that give us periods of 0G that can last for over a minute, I understand, and offer with a large cargo bay true 3-dimensional motion. This has been used to get students some understanding of what zero G is like, train astronauts, test robots, test systems, but ultimately the joyride ends and a lot of people get sick, not because of zero G, because you're ultimately cycling between zero Gs and more than 1G during your trajectory. So the time limit really is the big deal, not to mention that it's not really cheap to get an aircraft capable of taking experiments up, ready to go and fueling it and so on. The balloon or blimp or drone flights, balloons and blimps, I would say offer 2D plus motion because you can't arbitrarily move them in that third dimension. The drones are better. They give you 3-dimensional motion, but with a quadrotor, for example, you still only have 4 actuators, which is an under-actuated platform, which means that you still have vertical constraints and your payload is limited. Now, everything has limitations, so I'm not going to suddenly point to this neutral buoyancy and say it's awesome. What I'm going to say is that the WISE space simulation researcher will collaborate and try to pull the best from each of these environments to make sure that the collaborative group gets the best data and integrates it into data fusion, machine learning enabled systems. I know I'm using some buzzwords there, but the reality is with the parabolic trajectories, you really get the people and the robotic systems kind of together in an environment where they truly have that floating experience that's not just underwater. So neutral buoyancy has been used by NASA for a long time and others. And the reason for that is that you can have very long duration floating experience and you really do get full 3-dimensional motion because if you're neutrally buoyant, including an attitude not like having a keel on a boat or a submarine, then you truly get 6-degree freedom motion. But you have water drag, and so you never get that ability to, once you start moving, you keep going because it's easier underwater than it is in space. If you accidentally apply a force, then your counter reaction, it doesn't matter much because you have drag. So that still has limitations, as does the necessity to waterproof everything. So the propulsion type, the waterproofness, and the drag are completely different between neutral buoyancy. And neutral buoyancy itself is cheap per experiment, but very costly per facility because you have to build the tank and take care of it over time. Gantry platforms, like as what's present at the Naval Research Lab near Washington, D.C., are great for proximity operations because they offer you a low drag way to get the payload and the satellite, or the robot and the satellite, close to each other to do things like rendezvous and docking and manipulation, for example, satellite servicing. But you don't really get to explore guidance, navigation, and control accurately because you have to effectively simulate what you think would happen with free-flying spacecraft and robot because you have fixed base robots on both sides governing the motion. So this is my last slide. I hope I'm not running too long. So what's next? Well, these are all things that other people have discussed, I think, at least the first two. Europa mission with the Jet Propulsion Laboratory leading it requires autonomy. There's going to be a multi-stage spacecraft deploying I'm not going to call it a lander, a splashdown element, a module that's going to descend and collect data as it goes down. Communications, autonomy, very challenging, not only because of the delay, but also because you have to get all of your data and make decisions on it in situ before you ship it back to Earth. There's very little time. You really can't have mission control supervision of that mission. Venus has been proposed as a mission where a lander, because of the chemistry, the atmosphere will corrode, and I said die, right? It'll cease functioning in hours. Well, is it worth it? Well, one of the reasons we don't hear so much about it is that it's really unsatisfying to spend a lot of money and then have a lander that only lasts for a few hours. But science-wise, there's a lot to see. And there it really pushes the autonomy also, because you have to get all of the data and move it up to whatever orbiters or other assets you have access to within the hours while the robot is alive. So in terms of Moon and Mars, you have to have autonomous robots to have efficiency. I talked about that before. I'm not going to keep going because I think I'm running low on time. The last point I think is pretty important, even as researchers, because there's such a small amount of the population of engineers and computer scientists in the world that are working on space robotics and space missions. You have to breathe deeply and try to be as effective and progressive as possible in not only demonstrating, but deploying to maximize true productivity in space. So I was there as a young student in the 1980s. We were talking about the same space robotic missions that we're talking about today. We still haven't done them. It's 40 years later. We have flown demonstration missions to do things like rendezvous and docking, and they've been successful for the most part, but we're not actually using them in meaningful ways yet. So as we do research in space robotics and space systems and communication, we have to think about not just the demonstration, but also how to be productive in deployment, and not just one-off deployments, but routine deployments, kind of like what we've done with CubeSats. So to do this, there's a couple of ideas here. First of all, we need to figure out how to take all of those rich data sets for things like self-driving cars and autonomously landing aircraft and Earth observing science data collection, whether it's by balloons, spacecraft, or ground-based weather stations, and understand how to take that data and apply it effectively to space. Maybe we set up communication networks where assets are operated in degraded ways with the same kind of disruption in service that you would expect in space. Now, I know most people kind of already do that. And is the data realistic? One of the challenges of machine learning is when you do simulation, whether it's just with code or with a combination of real world data and code, are you getting it right? That's hard, but it's worth discussing as opposed to giving up before you start, because we don't have much data from space yet. For science, we have a lot of data. For engineering, not so much. But one of the things that is common is that in space robotics, we have a long legacy of mission operation and teleoperated practices and an inherent distrust of increasingly autonomous missions. We have to get past that. I think the way we get past that is not only the demonstrator missions, but by maximizing the tech transfer from the increasingly autonomous robotic assets on the ground and deployments on Earth to space. And I think we'll get there, hopefully, while I'm still alive, because 40 years from now, I don't know that that'll be the case. So this is, okay, I have one more slide, right? Some of it is repeating, but that's asking more questions, right? How do we take everything we know about Earth, including the space simulation work that we've done on Earth, to apply to space, and really think about what is valid and what is not valid for the application that we're targeting, right? So this is for things like guidance, navigation, and control, human-machine collaboration, AI, machine learning. We know that the spacecraft and the robot designs need to change, but what do we focus on? We know that we have to have radiation hardening, thermal, in some cases, thermal protection and so on, but what about the actual robots themselves? An example of something that my colleague Dave Aiken at the University of Maryland was very fixated on, and I personally think he was right. He was building Ranger and its tool suite in parallel with NASA Johnson building Robonaut. And NASA Johnson built Robonaut with a hand, right? That looks like the human hand. Now that was really great for PR because you have a robot that looks like a human, and that's kind of compelling. But why are you making such a complex actuator system to grab things and fix things? Well, the reality is you get a lot less productivity when you insist on something looking like a human hand. Well, the counter argument is, if you have a robot up there servicing a spacecraft that was designed to be serviced by a human astronaut wearing a glove, then it doesn't matter what you want in terms of an optimal tool. What matters is that it was designed for a human-held apparatus. And so you have to have the hand because you expected an astronaut with a hand to do the job. But now we think about modern robots where we're not expecting to send an astronaut up to do something with a Starlink satellite, right? That would be just out of the question. It's not going to happen. So now we're beginning to deploy lower cost assets where we either just discard them, like this cup. If I break it, it's ceramic, I'm not going to replace it. I'm going to replace it. I'm not going to fix it. Well, in space, do we always do that? Do we just let everything burn up and crash, or do we actually try to repair and refuel? If we're trying to repair, upgrade, and refuel, then we need to design these systems to have the optimal tool interfaces so that a robot, an autonomous robot system, can do all of these things. So that's something that if we want efficiency and disruption, we just have to breathe deeply and do, as opposed to putting things together that really can't be serviced in space at all. And then finally, the data sets, right? If we want to look at true autonomy and effective human-machine collaboration, we need to think about leveraging many different test beds and deployment scenarios on Earth, rather than basically arguing that the one that we have is the best. And to do that, something like having a group collaborating that has multiple assets to do testing, data collection, processing, and then fusion of that data and the results, that's going to be the most effective. And I know this workshop is mostly on communication, so I appreciate your patience with me talking about space robotics, but I think anytime you talk about something like communication, you want to ground it in future missions, and space robotics, I think, is an important component of that. Thank you. This is where great silence makes me very nervous because I'm afraid you're all asleep.
No, we're good. Can you hear us?
Yes.
Okay, great. So I think we have time for one or two questions, and you want to do one online and then one in the room? Yeah. So the one question online was, how much zero-G testing is done on the space station, and are there any, as I'll just put my own spin on top of this, as the space station as a national lab, right? Is there any thoughts for how do you do remote access, or how do you allow other people to run experiments who are not physical astronauts up on the station?
Yeah, so certainly in the realm of science and education, there have been a lot of attempts to have remote access where there can be even students talking to astronauts to kind of be motivational in the education and outreach side of things. And obviously an astronaut or a system on the space station has to actually physically do whatever it is that the experiment is, but there can be real-time communication link with the appropriate delay to allow the group to be involved. There are, of course, kind of competitions for college level experiments on the space station that are kind of an extension of K through 12 outreach. In terms of the space robotics, NASA has been really hesitant to have low-cost space robotic projects deployed on an asset like the space station or previously the space shuttle, because there's a perception of high risk. So to my knowledge, the main two robotic systems have been the Robonaut system, which was Robonaut 2, not Robonaut 1, that was collaborative with GM after the first generation, that has been IVA, intravehicular, and then Spheres, which has also mostly been IVA, but maybe has been a little bit EVA, right? There's really a lot of nervousness in sending a free-flying robot outside the space station, because if the robot were to go rogue and start smashing into solar panels, it would be a bad day for the space station. Now, the reason that I say that is that I think I'm kind of replicating what I have heard from NASA for many years, that they don't trust autonomy, that they don't trust robots that have not been extremely carefully vetted and proven. And, you know, Spheres was started by a group of MIT students, and there was a lot of maturity given to it between when the students did it for a senior design project and when the vehicles went up into space, but they're still not used for general purpose inspection. So what does that mean? Well, it means that while we've gathered a lot of physiological data about the astronauts, and we've gathered a lot of data for astronauts on EVA doing specific tasks, we have not really had an open environment on the space station shuttle or any other vehicle for long-term space robotic experiments.
Okay, great, thank you. And then while we're getting set up, are there any other questions for Dr. Atkins in the room?
If you got any other questions, I can wait, but I was going to abuse my privilege.
Okay, please go ahead.
Dr. Atkins, you said you have Starlink somewhere in a farm in rural Virginia, which I was wondering if we could impose on you, because we have this active measurements testbed that we're setting up.
This is why we invited you, Alice.
Hey, you need me to collect some data? Yeah, I'm happy to do it, right? And you know, you're going to get data from that antenna on my 1977 Dodge truck, and all that I ask in return is that somewhere in your materials that you put this picture of my truck in your.
Absolutely. It's a great red truck with a Ford truck, I guess. Well, thank you very much.
No, it's a Dodge, but it's still a good truck.
It's a Dodge. Okay. Well, okay.
Yeah.
Great.
Yeah, sure.
Okay.
Be happy to do that. You know, please, if you don't have my email address, get it from John and send me something.
I think I have your email address. Yes. Yeah.
Cool. All right.
Thanks. Well, anyway, John is going to be sending you the Raspberry Pi, I guess, because of customs and other things. It's hard to send across, as we found out painfully, to send across countries. So what we do is get someone in the other country that we know of conveniently, and they send the actual hardware to you. So.
Sounds good.
Right, I guess you'll be staying online for the panel. What we'll do now is the panelists will come here and get set up and give maybe 2-3 minutes for people to stretch their legs. I know we're running late, but it's been a long session, so I'm sure some of you will probably want to get a tea or a coffee or something. So maybe give 5 minutes and come back here at 4:40. And in the meanwhile, we'll get the panelists to get set up. So just to remind everyone, this is the funding panel where people are going to talk about the opportunities that are available from different funding agencies. And then 2 academics who started and ended the workshop, Gori Fairhurst and Ella Atkins, respond back to the opportunities on offer, reflect on their experiences in their long careers, and then any questions that anyone has online or offline, it'll be a free for all, basically.
Oh, right, okay. I was thinking.
Because you're in the space, you're in the sea,
It's a
in the
wild
ocean.
world out there.
Okay, I guess if people are ready, we can get started here. Thanks for bearing with us until the very end of this workshop. We are running a little bit late, but I think there were several interesting talks. It would have been a shame to cut them off. So thanks for bearing with us. So what we have here to end the workshop with is the idea was to bring these two communities together, the satellite and the aerospace engineering community with the communications and networking community. And as we all know, funders want us to do interdisciplinary stuff, and that is not easy. And oftentimes we may not be aware of all of the opportunities that are on offer from the multiple agencies that might be having an interest in this space. So what we've done is we've brought together a number of them. A couple of people are going to be online. So Dr. Deep Mehdi is joining us online. So what we have is we've got 4 funders and 2 academics who are going to be responding back to that. So we're going to do the offline ones first with the funders. Then we're going to have Dr. Deep Mehdi have his opportunities on offer advertised. And then we're going to have the 2 academics with long experience respond back to those funding opportunities, reflect on what worked and what did not work for them during their careers. And then we'll open it up for questions from everyone, online and offline. So let's start perhaps in the order here, but with Deep, maybe we'll put you at the end so that the online-offline transition is minimized. So let's start with Laura McDonald, who will be talking to us about what EPSRC has on offer. So EPSRC is, for the people who are international, EPSRC is the UK's Engineering and Physical Sciences Research Council. And I will let Laura say more about what EPSRC is and what she has to offer.
Hi, so I'm here representing EPSRC, Engineering and Physical Sciences Research Council. Oh, sorry. Hopefully you can also see my email address at the top of the screen. So if you've got any questions following this that you don't want to share in as public forum, you're welcome to email afterwards. So within EPSRC, we've got 2 sort of streams of funding. Okay. Yeah, sorry, I don't have a shirt lapel. Okay, so we've got 2 streams of funding. So we've got discovery-led research. And as you can see, this is the blue skies research that I think most of the people in this talk are interested in. So this is the community-led, looking at sort of landscape mapping and where the exciting new ideas are. And this is coming from our community. This isn't something that we are having from government or that we're deciding to do from our strategic advisory teams. The mission-inspired research you can see at the bottom there, things like engineering net zero, AI, they're coming from government priorities. And obviously this is the space, the bottom line is where you're seeing calls, and the top line is where we're seeing things through standard mode, so through applications you can put through throughout the year. Within the ICT theme, and I will come on to in a second, but if you fall outside of this space, you probably are still eligible for EPSRC funding, but this is the theme that I work within. We fund things through AI, photonics, language processing, Internet of Things, cybersecurity, things that formerly fell into the DE space. We fund things like new architectures. So it may well be that if you're doing something really fundamental within this space, it's worth getting in touch with us. But wider than that, the top circle, the orange circle there, you can see that's within the ICT theme of EPSRC. But as you can see, there's a big crossover with the AI and robotics, digital security and resilience, which is a new theme we're developing. And obviously we work closely with the other themes across EPSRC and with other councils across UKRI. So if you want to do something that doesn't sit nicely in ICT, that's not a problem. You can put your research funding into us and we can see where the right place is for that grant. If you are applying for standard mode funding, or if you're thinking that you would like to apply for standard mode funding, and that includes standard grants, network grants, travel grants for working with other academics, and includes new investigator awards and fellowships, you need to align to one of these priorities, and they're very broad. So next generation computing, sustainable ICT, future comms, people at the heart of ICT, AI and data science, and trust and security. So you can imagine that certainly within this room, all of the research we've seen presented fits really squarely into these priorities. We also have, this is standard mode, things that you can apply for all year round. We assess proposals every quarter. So you can have a look on the website, grants on the web if you want to see what we fund. On the back of that, we also have things that we are looking at in terms of calls. So these are priorities that have been identified either by government, research community. At the moment, we're developing a call in future communication systems. It's going to look at the networks, AI, wireless access, materials and sensors, security, global coverage, resilience, and sustainability. So it's going to be quite broad. And if you keep an eye on our webpage, you'll see opportunities to engage with us about how these calls are developed. We also have a priority around sustainable ICT. And as you know, we've just had Net Zero Week. We've done a lot of work around Net Zero and COP26. This is off the back of that, looking at materials, but also looking at architectures and low powered tech. So I think there's a lot of people in this space that have relevance here too. We also have the Future Networks Initiative, which is a call we're developing, looking at 6G, and it will be working with India. So please keep an eye on our website. Again, there's information coming out about this. It's a call we're in the process of developing, and it's very likely to be of interest to people in the room. Currently, we have a call open around enabled human-centered decision-making. So this is on our website. It closes at the end of August. And if you have any questions about this, please do get in touch, because obviously time will be a little bit of the essence. We have also got lead agency agreements with other countries. So if you want to put a grant in through standard mode and you want to work with an academic in a different part of the world, if they fall into these spaces, a lead agency agreement just removes the double jeopardy from applications. And I think NSF colleague will talk further about these. So I don't want to steal your thunder there. That's me done.
Next up, we've got Tom Kirkham talking about what Innovate UK has to offer.
Thank you very much. Perfect. Okay, so my name is Tom Kirkham. I'm an innovation lead for Future Network Technologies at Innovate UK. Innovate UK, like EPSRC, are part of UKRI. But we operate higher up the TRL level. So we tend to work with businesses and universities to try and bridge that gap between fundamental research and proof of concept kind of demonstrator projects. We see ourselves as a development agency within the UK, but we also collaborate internationally. So we do bilaterals, for example, with the US on specific topics. And we also support a lot of the European funds within the UK, which I'll go into detail in a minute. So looking at the UK side, basically we run funding competitions, as you would imagine. We've got quite a varied range of standard interventions. The main open one, like the EPSRC, have got an open rolling call, is called SMART. That's focused at any real sort of game-changing technological area of research and applied research into industry. Funds can both cover academic and industrial costs, and we tend to look for collaborations between the two. We've also got specific calls, and a good example here is this high altitude intelligence call, which is linked to HAPS, high altitude pseudo satellites or platform systems, however you want to define them, which is going to launch later on this week. That's a £4 million fund for industry again and in academic collaboration on those kinds of technologies. And we're looking to introduce more innovative schemes outside of competition. So we've got a fast innovation scheme, which is a very slimmed down competition designed for effectively startups. So academics within the room, if you've got any good ideas, it's a good opportunity to try and do a spin out. You can get a 50k award here for 100% funding rate, which is done in a very lightweight way. And the other supports we offer loans. Innovate UK Edge is consultancy support for companies. And we also do global missions out to markets all over the world. Now, EU funding, this sort of can be split into sort of two areas. So there's the Eureka program, which you don't have to, it's not limited to members of Horizon Europe. So Horizon Europe is the main sort of funding body within the EU, which we used to be a part of when we was a member of the European Union, but we've currently associate members, but we've not signed the agreement yet. It's a big source of anxiety. I'll go into that in a minute. But anyway, the Eureka clusters, that's open to EU members, but also Canada is a partner within that, Singapore, South Korea. A specific call, which is telecoms focused, is Celtic Next. Details are on the screen. If you want any more further details, my email address will be on the end, but I encourage you to consider the Celtic schemes because quite often there's a high success rate, and also it's a good opportunity to do a lot of collaboration with the contact points within the countries as well as the academics in order to get the projects up and running. So a quick overview of Horizon Europe. So current status is that we've not quite signed the association agreement yet, but we can still collaborate in proposals, but we can't coordinate. I'm sure you're familiar with this. European funding is a big source of funds for universities like Surrey. We've got a guarantee, so if you get funded by Europe, the UK government's offered to cover the costs. What that means in practice is basically if we don't associate, we don't go in as a member, but we go in as a partner, funded individually by UK. But they look to be making a decision by the autumn on the association now. I think these slides were done before last week when Boris Johnson resigned. So, but yeah, fingers crossed. I heard it was before the summer a few months ago, so it could slip. But if it slips anymore, I think the Horizon Europe scheme will probably be going into another one. So I'm pretty sure they'll be trying to make a decision soon. But it's a very serious issue for academics in the UK, and I'm sure the UK government's looking to cover our membership as associate partners if this doesn't come off. So quickly into space. As you can see, there's various different areas of focus, and the latest course coming out in October, split into 5 main areas. There's a big focus on satellite imagery and geospatial data linked into Copernicus, and also positioning as well. The quick overview of the calls there. I'll share these slides after. There's a work program going to be released in 23-24 that's been leaked, and it's again quite a wide-ranging area of focus, again from positioning, navigation, quantum's part of that as well, and Earth observation. So thanks very much. Quickly, there's my email address if you want any more information, and also I'm happy to share these slides. Thank you.
Can you hear me now? Yeah. So next up, we've got Fabrizio De Paulis from the European Space Agency.
Okay, if I'm over.
Yeah, of course. Yeah. I think you've got your slides there. So
Not because I'm important at all, just because I don't have the slides. Can you hear me okay?
very sensitive.
Yes. Better? Yep. Okay. Well, thank you all. First of all, apologies if I couldn't prepare a more technical presentation, but I'm happy that there were extremely good contributions today. Professor San, Vodafone yesterday, I think excellent. So it will make my life much easier. I will avoid to repeat anything that was discussed earlier today. Okay. Just click it. Okay. Yeah, I will just say that as far as 5G and 6G is concerned, which is a little bit my area, I think the main achievement we can all claim is for the first time, satellite communications are part of the 3GPP standards, both in 14.17 and the future release, I think. This obviously for us as a community is a very important news, as for the first time we're fully on board in the specification, in the requirements, and of course in all the technology development and the next steps that we are looking after. In our view is, of course, 5G and especially 6G is a three-dimensional network where terrestrial is fully integrated with satellite and vice versa. And on top of that, we have also an intermediate segment, the air segment, which support, of course, the deployment of the full network. It's quite obvious to us that in this context of integration of satellite terrestrial, there must be a variety of opportunities for researchers, for universities, and satellites will play a big role in our opinion. Just as a personal view, there are, I think, a number of areas that some will discuss today also in terms of, for instance, interference mitigation, antennas, MIMO, and 6G satellite architectures and technologies. This does not pretend to be, by any means, an extensive list, just a quick overview of the areas we are insisting or working on the moment. So what is the program that we discussed today and is more suitable for working 5G with the university and together with industry? Well, it's the ARTAS program. The ARTAS stands for Advanced Research in Telecommunication Systems. It is a partnership type of program where the ESA is seen as enabler of all the full funding mechanism, where you have, of course, the funding itself, but you have some kind of guidance from ESA in what is the most suitable programmatic tool. You'll see that there are many. There's not just one. You have some independent assessment from ESA, which we hope adds values into the discussion. We offer think tank for these opportunities, workshops, conferences. Of course, the review process when you submit a proposal to ESA is part of the exercise. And of course, we try to facilitate cooperation and synergies between industry, universities, and other partners. There are two main mechanisms, I would say, that could be interesting for the R&D community. And it is, the first one is probably the most attractive, is the advanced technology, ARTAS Advanced Technology work plan. This is an ESA generated work plan where, of course, everybody can contribute, especially universities. And it's basically a call for ideas where ESA coordinates the various contributions. There is an annual work plan that is published. Invitation to tenders are issued, and the bidders can submit a proposal to ESA and get a contract, hopefully. The good part of this is that these calls are that they're fully funded, and they're meant to support technology developments with a certain level of risk towards the product development. So normally we're talking about TRL 5 or lower. Of course, they're open competition, so the best proposal tend to get the contract. Of course, there could be some parallel contracts in some cases. This gives you an example of how the work plan looks like. It is the 2022 work plan, which is currently open. Some of these calls have been issued already, some will be issued later this year. As you can see, we try to cover a variety of areas from the 5G system infrastructure studies up to the RAN developments, the core network, the test beds, and as well as the some more hardware-oriented development, the user terminal, and also the 5G and beyond. So more in the 6G development. As you can see, we try to be general, but there are plenty of areas for growing. In the sense, there are many areas where I could hear a lot of very interesting contributions today, where industry can add value, and university in particular can add value. And the message I want to pass is that university can contribute to this work plan. It's not something we do ourselves in isolation. Actually, we welcome your contribution, especially in the areas where maybe we don't have the expertise or we need some of your help. Okay, this, apologies if it's a bit messy and complicated, but this shows the so-called ARTAS Competitiveness and Growth program line, which is where basically we try to co-fund developments together with industries and universities. And this is basically covering the developments which are a little bit closer to market. So that go up to TRL 7, 8, and 9, where the there is a business case, so that normally there must be an industrial partner as part of the application, but universities and the research center could be part of the projects. We tend to define 4 the main phases that have to be all part of a proposal, could be split, it could be cover only part of the product life cycle, or all of them, depending a bit of your situation. Here, I think this covers industry. I try not to spend too much, but whether I want to spend too much time here, this basically the message is that we are co-funding the development based on the SME or non-SME status of a company. But for what concern universities and institutions, I think maybe this could be more interesting for you today, is that the funding level is higher in general, depending on the technology risk that is associated. So we tend to fund 100% the technology phase development. But of course, there must be no commercial interest of the university or the research center. In some cases, if there is a commercial interest, the funding level is a bit lower, but as you can see, still substantial. The last thing I want to say today, which is really focused on the UK development, our UK center in Harwell, is the 5G hub. This is something I believe was discussed yesterday by Andy, so I won't repeat much, but I just want to maybe, I'm not sure if you had a chance to discuss, but just a few things that happened recently that are mostly R&D activities, some with universities, like the 5G demo with the University of Luxembourg over the moon, the Robodog being controlled by satellite in our hub, the Mars room, and other use cases we're looking for the next phase of the hub. So most of these activities are really cutting edge activities done with universities or very new startups. So this, I think, something could be very relevant to universities activities. I think just to wrap up, and then I'll conclude. We have, with the work plan, something that you can actively contribute, and this is fully funding developments to reach a product in the long term. The strategic line for 5G 6G in the product and technology development, which are co-funding lines. The 5G hub, which is of course open for business and for university. Of course, if you have any contacts and more, we're gonna go more in detail to the application process, and which is something, of course, that requires time. And feel free to be in touch, and I'll do my best to help.
Very much.
Thank you.
Last but not least, we go online, and I'll stop sharing the slides here. So maybe who's representing NSF. Deep, if you could share your slides.
Nishan, just give me 1 second.
Of course.
Can you see my slides?
Yes.
Okay, great. Actually, I focus mostly from a computer networking and space funding point of view, but I'm happy to talk a little bit more in general on the in terms of NSF funding and whatnot. So, okay, so I wish, by the way, I wish I was there, but I just got back from England about 10 days ago, and I had a panel, review panel yesterday and the day before. I knew there was no way I was going to be able to go back to, England to be at physically. This is an interesting workshop in terms of computer networking in space to see very interesting stuff. And I missed yesterday's presentation because of the panels, of which I was very interested in. So in terms of when we come to this area of computer networking space, it actually covers activities from multiple directorates. One of where I sit in is the Computer and Information Science and Engineering Directorate, which is, in short, we call it SISE, and Networking Research Program in the Computer and Network Systems Division. That's where I sit in. We actually cover a lot of things related to, obviously, any aspects of networking, from from the ground to underwater to all the way to space, and in that directorate, in all of it actually. The engineering directorate focuses more from there, especially the ECCS division focuses more from the engineering aspect of related to communication side of it, and that's where it is. In the case of Geo Directorate, they have the Atmospheric and Geoscience division. They actually look at a lot of things related to space communication. We actually collaborate with them quite a bit in terms of a number of different activities. And I'll give at least one of their project examples in a few minutes. And the Office of Polar Program, very interesting because they're located at the poles, and the communication to those places are very, very important. And so we also fund communication aspects to help facilitate all the work related to the Polar Program. So specifically, I'll mention a couple of solicitations. We call it solicitation when you create a specific program announcement for taking away from the general announcement. The ones I talked about above, all of those programs have what is called a core program general announcement. Anything under, you can say anything under the sun that you can actually submit proposal that fits into it, and in particular anything related to space communication. So as it fits into the program. The NSF SWIFT program, which is actually a multi-directorate program on spectrum and wireless innovation. And this one actually has a topic of interest, that the growing challenge of the coexistence between ground-based astronomy and large network of low Earth orbits, and so that's one of the areas that NSF, so the SWIFT program covers. The SWIFT program is in their third year right now. It's about $10 to $15 million program every year. Then another program we have, which is the Resilient and Intelligent Next Generation Systems. It's a pre-competitive industry partnership. We have companies like Qualcomm, Apple, Ericsson, all of them are involved. It's a $40 million program we selected, and where when we do the program, consider project for funding, then the industry has a industrial partners have a say in which one they would be interested in it. Again, I want to emphasize the pre-competitive funding, so they pitch in money into the program as well. This is one of very interesting, unique, sort of a government industry partnership program there. Again, when we say next year, it is broad. From it can be 5G, 6G, whatnot, anything. And so I do not manage that program. My colleague Alex Princeton and Rod Torlak does it. I don't recall if they got anything specific related to space communication in terms of the projects. In terms of a generally wireless area, we have the NSF Power Program, Platform for Advanced Wireless Research. This is a research infrastructure program. I have a separate slide to talk about power. It's about, again, partnership with industry as well. This is a $100 million platform projects, and that's a few of them are operational. We know researchers from Europe have been using it, and I'll talk about that in a second. I wanted to give you a few examples without going into any of the specifics. These are some of the computer networking in space example of projects that NSF has funded. CubeSat is one of the big ones, and it's actually the Atmospheric and Geosciences Division that has actually the lead on this one. CubeSat Ideas Lab, Space Weather Atmospheric Reconfigurable multi-scale experiment that they are doing it, and it has been ongoing for a number of different years. And you can see a project on, NEO geosynchronous satellite communication and radio astronomy system. You can see projects related to, scheduling in the, in a lower Earth orbit. So these are examples of different ones. The last one is interesting because we have a funding program called SBIR, Small Business Innovation Research. You can see there's a project on quantum key distribution via small satellites. So this is a very interesting program in terms of bringing small businesses involved with academic research to submit projects. This program was, until recently, has been run under the Engineering Directorate, but NSF had recently created a new directorate as of a few months back called TIP. TIP stands for Technology, Innovation, and Partnership. So SBIR is moving under that program, that directorate under the TIP directorate. Switching gear for a second, I want to mention something else because I saw a message in the chat. One of the TIP directorate's new program is called Pathway to Open Source Ecosystem, POSE. And in fact, I serve as a representative from the CNS division on that solicitation. We got our first round of phase 1 proposal that came in, and that's actually the panel I was busy last couple of days with. And so under that program, we are also saying different things, but I don't recall, at least in the panel, I handle anything related to space communications. Any open source ecosystem development in that space. But we very much want to see that taking off much bigger down the road with this program. So let me talk a bit about the Power program platforms. The Power, we have actually 4 platforms there right now. 2 of them are in the urban areas, Powder and Cosmos. Powder is in Salt Lake City, Utah, and Cosmos in New York City. And they focus on the millimeter wave and and software-defined network, the first 2 platforms. And then the Airpo platform is in Raleigh, North Carolina. It's related to drone networking and mobility, and so that's the one. The first 2 have been around for about 3 years when they started creating the infrastructure. Remember, these are infrastructure in terms of platform. Each of them are, $8 to $10 million range. So this is about $50 million altogether, I think, and then another $50 million in kind and other donations from industry partnership. Arrow is the most recent one we funded as of last year. This is on the 5G, 6G related to rural broadband and precision agriculture at the Iowa State University. And so in addition, we have Colosseum, this is the largest RF emulator located at Northeastern University, and the OAX and end-to-end open source 5G software lab. So I wanted to mention that because that has some implication in the context of space communication. I want to touch a bit on the US-EU collaboration. One of the things we work with is the EC DG Connect entity. And so, in fact, specifically, I've been involved with the NG Atlantic, which is the next generation internet, the Atlantic program. With that, they have multiple different calls in the last 3 years. And we funded a collaborative project from the NSF side that have partners from the EU side. Interestingly, several of those projects actually are experimental research projects, and they are using some of the Power platform I just mentioned earlier. This program is coming to an end because NGI Atlantic's term is going to be over soon. But in my conversation with EC, that they are looking to create a couple of new programs, and we are looking into how to expand that partnership on a bigger scale with a little bit more research-oriented thing. Beyond that, we have country-specific partnership, lead agency model. I'm just listing a couple of them. Finland and Ireland, for example, have the partnership with us. A lead agency model basically means that the lead, as NSF as a lead agency, does the entire reviewing of proposals that is submitted, and then whatever we recommend, that the science organ foundation of the other country actually agrees with that and fund their researchers there, who are the collaborators on this project. So with that, I'm going to stop it here, and I'm happy to answer any questions you may have. Thank you very much.
Very much. So now I'd like to invite the academics to respond back. We'll start with Ella, because to minimize the online-offline transitions, Dr. Atkins, if you could tell us your reflections on what you've heard so far, maybe some things that worked for you, things that did not work well, that people in the different stages of their career could reflect on and maybe useful to them.
Yeah, so I think in the US especially, one of the opportunities is to look for early career programs as an academic. So for example, NSF has an early career program that specifically is inviting assistant professors to apply. And it doesn't really matter what your science or engineering topic is. If you find the right place to send it, then you're competing not with people who have done the research for 30 years, but with peers who are just getting started as well. In terms of the funding, what I've seen is that there are more opportunities for extremely low funding, like student projects, getaway special type things, where there's not money to fund PhD students, but it's more teams, short-term, getting something done. And then at the other extreme for space is the full-on mission, where you're actually, no kidding, going to build and launch and operate a CubeSat or something like that, which is very high money. But I had a colleague at the University of Michigan who really taught me a lot about what that means. There's a lot more money for subcontracting and science than there is for aerospace PhD research. So I tried to say that carefully. So it's a great thing, you know, students line up at the door to go through all of those stages of research, development, launch, and operations of something like a CubeSat. And that includes communication, but certainly is not limited to communication. It's everything, CubeSat system, including the science. And so the main benefit from that is having undergrads and young master students who want to go into industry really be exposed to a realistic end-to-end development cycle, including operation. There's really no substitute for that you can find in a lecture-based classroom or even a traditional lab course, because that process really can't be replicated without having legitimate, no kidding hardware to work with through that whole process. So those programs are really exciting and have had some opportunities for you know, a number of people. And the CubeSat is a great platform because it's small enough that it doesn't take a whole team of people in a clean room to put together, which is not really feasible for academia. So CubeSat missions are awesome, and I hope they continue. There's also a lot of lessons learned, even if the CubeSat itself doesn't do what it was supposed to do. It gets you away from this notion that everything's doomed to succeed, right? If you have a homework problem, if you have a lab experiment, then you have high expectations that it's going to work. With the CubeSat, if there's a mistake made, sometimes the thing doesn't work. And it really is a hard lesson, but an important lesson, that in space, the environment is forgiving and whatever you send up is going to do what it's going to do. So those are great things. I'm going to talk. You've called me old and not in a bad way, experienced, I believe it was, but I'm going to go back all the way to the 1980s, 1990s, and 2000s to look at the cycle of space robotics research and specifically funding by NASA in the US. In the 1980s, it was awesome. There were centers. I was part of one of them as an undergrad and master's student that I felt like it was just a well-funded, great opportunity, and I learned a ton. But politics get involved because, how do I say this? At least at NASA, there's two high-profile moneymakers. One is science, because we need to pursue science. And one is manned spaceflight, because we need to explore. What I watched when we had various changes in US leadership was for the administrator of NASA to come to university that I was at the time, University of Maryland, and basically say, oh, and by the way, he was an alum there, and say there will be no space robotics funding for a long time, or space engineering funding, and everything was canceled. And that taught me that even though you may have worked hard to get a funded grant, that if you're in the middle of politics, it might not finish. To their credit, in the US, the National Science Foundation doesn't tend to do that. They tend to keep going with the grants that they've promised. So it's something, and NASA with their young investigator grants tend to keep going as well. But what did this mean? It means that, like, even reflecting forward to the CubeSats, there's a really interesting dynamic between the science investigators and the engineering investigators. And at Michigan, they're right across the street from each other. So there's a lot of joint meetings where you get to see this dialogue up close and personal. If the scientists feel like the mission is for the scientists, they don't really see the PhD level research value in the engineering. And it makes the dynamics hard. Who's going to be PI? Where is the research money going to go? And I am pleased to say that I have rarely been in the middle of that discussion. I've been a spectator watching it. But I think one of the things that's exciting, at least about space at VT that I've seen so far, is that there isn't that dynamic, right? It's not competitive within the institution, it's more collaborative. So I think as long as everybody sees the value of the others, right? Don't get the blinders on, right? Communication systems, and I know I'm addressing a largely communication audience, are super important, but they are one element of the greater system. And so it's so important for science, electrical and computer engineering, which includes communication, the engineers designing the spacecraft and making it work, and everyone else to really truly respect and try to understand what the others are doing. And that's not a funding thing, but it is indirectly, because a cohesive team is going to build itself into a position to be better able to compete for high value monetary support. Through centers, through missions, and combinations, I guess I would say. I don't think that it's really easy to do that. There's a lot of interesting dynamics. I know in the US, there's increasingly a need to ask for support from industry, because there's a lot, at least over the past few years, of venture capital funding that can be available, not only for small businesses, but also even for some university entities that are working closely to help develop a technology that the larger small business needs. And so that hasn't, I don't have slides for that, because that's really very specific to who you're collaborating with. But as these new businesses spin off and develop, it's really represents a great opportunity for academic researchers to stay involved, not only to support their former students as they struggle and succeed with their businesses, but also to make sure that there's a good synergy between what's being taught and researched in academia and what's being transitioned into practice. I think this is very vague because I don't have money to give, so I'll just stop now. But it's always a challenge to go from having a great idea to getting money to actually pursue it in a substantial way. And each researcher has to find their own path. But there's, again, especially if you look broadly in the definition of where the money comes from and how you can do research that feeds into the space product that you dream about, you're going to find it through some combination of government, alums, even industry, and other sources, fellowships, and all.
Thank you very much. I'd say experience is worth much more than money. And I'll hand over to Professor Gauri Fairhurst to reflect on his views of what he heard and his experiences so far in his career.
Okay. Is this mic working? Is this mic working? Yeah, okay, cool. Right, okay, so I agree with Ella on absolutely everything she said apart from one thing. I think actually the communications payload can actually be the biggest and most exciting thing that's been flown. Maybe the TT&C and the support system, the launch system is just part of that solution. So that rather depends on perspective only. Everything else I agree entirely with. And I think the first thing I'd say is just looking back. 4 or 5 years ago, I probably was away from the space industry for a little while. I was working on EU funded projects with the Internet Core, and I've come back, and my goodness, things have changed. So we have all this LEO activity. That's really exciting. We have MEOs actually in production, offering real networks, and we have huge advances in the geospace as well. We shouldn't neglect the fact that the geobirds that are now flying are very, very different creatures to what we've seen in the past. So 3 satellite systems and new opportunities to go to the moon and other places. This is a really interesting place to get into if you are seeking to develop a career, seeking to inspire your students, or just wanting to get money. To do research, yeah, I've not put any money ever from NSF as far as I know, but I've taken gratefully for each of the other funders money in different forms, and there are many ways to get that money. And one of the real difficulties and challenges is working out the right instrument, the right thing to apply for. You might have a great idea, it might be a great research idea for a new algorithm, a new method. Who's interested? I mean, if you look at the list of things, you don't often find what it is on their list of things that they wish to fund. Somehow you've got to bridge that gap and talk to them and find out who is willing to actually fund the research. It's a little bit easier, perhaps, if you've got an engineering problem and you have a company, because there's plenty of engineering problems here. They require you to actually work with a company. You might have the best research idea, but if you can't find a company and get them to talk to you, that's a real problem. But this community, I think, is also a community where you can actually meet people. So there are ways of finding the companies that are interested, and usually they have the same problems as the ones you're trying to solve. And I guess finally, the last area where I've got funding from, which has actually been probably the most inspirational from the educational perspective, is just jumping on board some of the application projects of using our technologies. I worked with the London Symphony Orchestra with musicians playing remotely. It was a small ESA-funded demonstration. My goodness, lots of people were interested in this. It was a huge activity. It stimulated a lot of people. We got news time on the TV. You know, that was a big project. I worked with a group of archaeologists using a new broadband satellite technology in a really rural area to highlight the idea of connecting the rural people. And again, people were inspired to think about the rural divide and the funding there simply because we did a demonstration with them. And the students involved, well, they learned a lot. So there are opportunities right throughout this spectrum, and space is a wonderful place to actually pin your future research on because it's got that application which is attractive. It's got the engineering where real engineering work is done. And yeah, you do have to know a little bit about how to launch a spacecraft and what its constraints are, as well as all the communications part. And of course, there's all research going on, and some of that is really interesting at the moment. So I'm trying to be positive, but I know it's not easy. So please talk to the other people on this panel about how to make that happen.
Thank you so much. Yeah, I can second that with some of the smaller projects, even if the money is not big, it's often the most attractive or the most personally satisfying projects, and perhaps the most impactful as well in the end. So I'd like to open up the floor for questions, whether online or in person. Anyone would like to go first? Okay. Maybe introduce yourself on that.
This is Arun Sen from Arizona State University, and this is for Dr. Mehdi. Dr. Mehdi, you know that this workshop is about computer networks in space, essentially satellite networks, and new communication technology that's developing, which has not been discussed very much in this workshop, which is quantum communication. And the quantum communication is going to play a major role in satellite networks. So if we have and it's just not about quantum key distribution. There are other aspects of quantum communication where the satellite networks are going to play a major role. So my question to you is that if we have a proposal on that, which program would be most appropriate for submission?
Thanks, Dr. Sen. So let me see. It's been a few years since I saw you, I think.
I was hoping that we see you here.
Yeah, I've not been in Phoenix in a while. Let's see. This is, if you're going more on the quantum networking side of it, you can submit it under our CNS NETS core program. In fact, we do get a few proposals in that. And we, as I said earlier, our core program is open to any ideas, any new thoughts. So we actually did handle a number of proposals related to quantum networking in the last year. It's not a big pool of proposals, but we do get it and we handle it under our core program.
So NSF now has a big thrust on quantum computing. I think there are a lot of things going on there. So I was just wondering whether CNS would be more appropriate or going to that program would be more appropriate. What's your thoughts on that?
Well, I mean, the thing is that more from the perspective of whether you are going to the networking side or the computing side of it. If you're going to quantum networking side of it, obviously CNS core program, specifically NETS program is the right place. But if you're going more on the computing, then, on the quantum computing, even the director of mathematical sciences is involved and all of the different players are involved because that's, quantum computing was a part of the 10 big ideas that NSF created about 8-10 years back. So, it's just a question of how you're orienting your proposal and where. One thing I'll add to it, Arun, is that please contact program manager if you have an idea with a short one-page write-up, and we can then also direct you if there's a better program to send your proposal to.
All right, thank you so much.
Thank you.
I just noticed in the chat, Laura, you have posted about the NSF connections. I wanted to give you a chance to say if you had anything more to say about that.
Okay, yeah, sorry, there was a question in the chat that was asking about, you can hear me. There was a question in the chat asking about lead agency agreements. So EPSRC and UKRI more generally have lead agency agreements with various countries. Someone asked what the limitations on these were. So he said, why is it only these themes or why is it only little bits of the sort of research landscape that's linked up with other countries? They're negotiated by the heads of theme and they have to align with the research priorities of both countries. So you'll have seen in the past, we've done, for example, engineering calls with China. We've worked really closely with other countries to look at priorities that both governments felt were a strategic need. Now, given the current situation, as we discussed with Europe, that we won't discuss further, we are looking to negotiate other lead agency agreements. And I know that UKRI is looking to expand the scope of our current NSF arrangements. But if you are looking to do work with America through EPSRC, you can, as long as you are within the remit of engineering, mathematical sciences, ICT, or physical science, you do have a lead agency agreement in place, but you will need to speak to your portfolio managers, just check what the remit of that is. Equally, because that system exists in the UK, you could choose to put your application in through the NSF rather than putting it into EPSRC. That would mean that, and either way, the application only goes to panel once. So as long as you've got an American collaborator, the proposal only goes to panel once, and then whichever agency didn't hold the panel just pays the section that is theirs. So we work really closely with our colleagues at different funding agencies. And again, like for certainly within ICT, we've got arrangements with Sao Paulo, with Luxembourg, with the NSF, and we are putting in place other opportunities to work with different countries, either through specific calls or lead agency arrangements. So please watch this space, and if you're not sure, just drop us an email. I know as well, this may not be relevant to people in the room, but just in case you've got colleagues that are interested, AHRC, ESRC and NERC all have lead agency agreements for some aspects of the work that they do, but just unfortunately, the two funding agencies, UKRI and the NSF, do not match up beautifully, which is very unfortunate. So some things are slightly out of the remit of one or the other.
So essentially, the UK is the same as Finland and Ireland, which were mentioned in Deep Stock. Okay, fantastic. And like another thing which I saw, there's a lot of discussion about open source and funding of open source. And Fabrizio, I posted on your behalf the open source simulator thing that you have a call for, which I just was talking to you about. So if you care to say something about the open source and what ESA might be doing in that space and open source simulators and things like that.
I mean, that's certainly a very interesting area, and we have, I think, a number of opportunities open. I'm afraid I cannot discuss much on the specific one because it's open, and there are
perhaps more in general about open source and how we could work with open source and ESA. And I think and maybe I could throw in one more question in there, because what I've heard from talking to several people in the last year and a half, where I've been getting more into the space networks, is, oh, space is critical national infrastructure, and there's all these laws in place that mean that maybe some of the work that we do can't really be open source or can't really work across nations even, because each nation wants to protect its space interests. And of course, ESA works across European nations, at least, some of the European nations at least. So I don't know how you see that. But when I look at all of the things that when the new buzzword of new space gets used, it's all companies coming in and just doing things without waiting for governments to step up their space missions and programs. So where's this role for open research in all of this, and what does ESA, how can ESA support that, I guess?
Yeah, I think it's a very valid point in the sense that our role is a bit to balance the need of open source in general in many areas, including Open RAN and other things, with the industrial and the national needs, let's say. So what we have a variety of programs that try to fit each specific customer, if you wish. So we have programs that are dedicated to national, or they're very aligned, let's say, to national needs, and of course they try to go in a little bit in line with a specific country or member state need. Web source, GOSACOM, for example, or other things of this level. Or the more ESA-driven initiatives that tend to be a little bit wider, and that's where we try to take everybody on board and to have a truly open source solution. And I think particularly in the 5G domain, we have an opportunity to have to go towards more standardization, and at the end of the day, you need to have open source from the high level up to the equipment, the ASIC, to have interoperability between the various users, and so that's how we're trying to. So in general, we try to tailor the particular program line with the national or ESA, let's say, needs. That's a bit our limitation and our strength. We try to we need to accommodate everybody, and so we have programs that will be flexible and tailored to specific requirements.
Thank you very much. I see there's a question online about how much ITAR blocks collaboration. I don't know who wants to take it. Perhaps somebody from the US, as maybe Dr. Mehdi or Dr. Atkins, if either of you have some experience with that, or somebody in the floor, maybe.
Yeah, so I actually, in my experience with commercial and exploration and science, ITAR doesn't block collaboration as much as do proprietary interests. So I'll name some companies. So I've, for example, early on visited Blue Origin, and they were interested in me coming there and doing sabbatical, but they explicitly said, your students will need to come here, and when you go back, you can't talk about anything. And I said, no, thank you. I'll be happy to send students, but I'm not going to like stop my research at the university so that I can go do secret stuff. And when I say secret, I mean proprietary, not classified. Certainly, there's a lot of Department of Defense work in the US, including a new Space Force group that's been set up. And I don't know a lot about that. They would certainly have a lot of ITAR information, but ITAR is not specific to space. There's a ton of ITAR just related to the type of work that you're doing. So for example, when I started doing autopilots for unmanned aircraft, I was told that an autopilot was automatically ITAR. And I was like, what about ArduPilot, right? It's open source, it's available to everyone. And they're like, well, autopilots are ITAR. And we went around for a little while, and eventually they went away and did not acknowledge that there was this stuff that was open source, but that was strange. That was just the way it was. And so I've dealt with ITAR successfully as a researcher by having the research office at the University of Michigan and Maryland, and presumably in the future, Virginia Tech, just deal with it. And when I say just deal with it, there are processes by which ITAR research can be done. I have a project ongoing right now that will end later this month, funded by the US Army, that has restrictions on citizenship and where and how you can put your data and process it. And we live with them. And it's up to each investigator to decide whether it's worth it or not. Some people decide that it's not worth it, in which case you just have to find your money from non-ITAR sources, right, to limit what you're doing. But there's a lot of basic science that is completely open. And so there is a place to go if you choose not to do the ITAR work. And if you choose to do it, my experience is that the university research admins and legal offices know how to deal with it now.
Thank you for that answer. There's a question. I'm not sure whether we have the expertise in the panel, but I'll just throw it out anyway. There was a question about whether Canada has any funding for space comms research. Okay, yeah.
Yeah, I can say briefly, yeah, Canada is an associated member state of VISA. So particularly for telecommunications, there is Canada contributes to ARTES, to program I was explaining before. Unfortunately, the budget is not substantial, but we can work together to increase it. And so the answer is yes, there are things we can do together with Canada. We've been doing for many years, and we can do more for sure.
Yes, that I expect that there was this capability. And I'm not sure if this is this on? Probably not on. Question about whether this is a question from this is not on here. Okay. Restart and then everything starts working. So there's a question about, I'm not sure if this is a comment from Dave Tat, could there be an ITAR clearinghouse for those outside academia? So probably a suggestion / comment about how to make ITAR work across ITAR. I think we are getting to the end, but I wanted to get a sense from everybody in the panel, because there's quite a lot of things that are similar, but also distinctions between these funding agencies. So for example, TRL is a good way to decide whether you would want to go towards Innovate UK or ESA or EPSRC, certainly within the UK. So if I could get each one of you to maybe say how what distinguishes you from other funding agencies that maybe the same set of researchers could apply to, and then how we might best position ourselves or think of writing a proposal for your funding agency as opposed to the others. Not putting you up against the others, but just the distinguishing factors, just so that within our minds we can clear it up as to what would be the most appropriate source. Maybe we can start with you, Tom.
Okay, thank you. So what distinguishes Innovate UK is that we're higher up the TRL level, so it's more collaboration with business. But my top tip when looking for innovation funding is to, really look wide on the landscape. So in the UK, DCMS fund a lot of communications research, and also we mentioned Eureka as well. There's a lot of money in those calls, and they're not as well subscribed as some of the ones that go down the Innovate UK route. So it's always good to look around the edges at funding opportunities.
Thanks, Tom. I think to complement what Tom said, ESA is slightly, I think, wider. We have a variety of tools. I spoke today mostly about ARTES, but we have also others for lower TRL, for instance. For what ARTES and telecommunication are concerned is that we look for commercial opportunities. So we need to have somehow product development vision in any of our ARTES development, whether it's a lower TRL or medium or higher. And we try to be partners. So we're not just giving grant, and so we're really part of the development. We are involved in the projects. We give feedback. Sometimes we are a bit hard, but we try to add value and to support the development also technically and with our understanding of the market.
Okay, so EPSRC is the fundamental research funder. So if you want to, you can think of EPSRC and Innovate UK as sort of the top and bottom of a research sandwich in the UK. And then between us, we've got the other research councils that fund things, usually that have come through the fundamental science route and then are now applied. So that's usually where we see our impact. We fund things that are truly fundamental up to the tech readiness level 3. But if you're not sure where your research fits within UKRI, we do have a remit inquiry service. So there's an email address on our webpage. You can send us a one-pager saying, these are my objectives, this is what I want to do. Can you just let me know which research council I should apply to? And we can do that for you, that's not a problem. But my biggest sort of piece of advice to anybody that's applying for research funding is please speak to your funders. We're here, we're very approachable, we're quite nice people. And if you give us a ring or drop us an email, we will help you to make sure that your research ends up in the right place. And if we can support you with what you want to do, we will do our best to do that. Ultimately, within the research funding landscape in the UK, we want to spend all of the money that we get from government on projects that benefit the UK and that benefit the research landscape. So if you're not sure what to do or how to go about applying for something, please just get in touch with us and we will help you to do that.
Dr. Mehdi to say about NSF and
yeah, we're also very approachable, like my counterpart UK said. I think as I said earlier, please send us a one-pager to with your ideas. We can then direct you to the right place. NSF as a funding agency spans a very broad things from fundamental research all the way to small business innovation thing I just talked about in my brief presentation. And so we also have the new directorate called Technology Innovation and Partnership. So I think, we are very broad in that sense compared to other federal agencies. And obviously we are, I want to clarify, NSF only handles non-clinical science and engineering research. So if it is more clinical oriented, you have to go to National Institute of Health. Obviously, the other agencies are more focused, like Department of Energy or Department of Defense. Those are more, some of them are more deliverable or product oriented, but NSF is very broad in terms of its space, from fundamental research to small business thing I talked about, or the open source ecosystem that we created. So it's a very solicitation specific thing we do, but when you have an idea, you are not sure where to go, you can always write to us and we'll be happy to direct you to the right place. Thank you.
Thank you very much. And maybe on that note, we will close this workshop on the panel. Oh, sorry. Corey wants to say a word.
Well, I'll let you close, but I was going to say a word of thanks to you for organizing this. I think this has been an amazing event, and my only plea is we should try again to do something like this soon. So back to you to close.
Thank you very much. I've learned so much, and it's not just starting from things which are being deployed for 20 years and experiences all the way to LunaNet and what we might see in 10 years from now, and all the wealth of funding agencies which came here to say all the opportunities on offer. So, and thanks to all of you for helping making this happen. And well, I guess we'll hope to stay in touch. What we're also aiming to do is set up an email list for this. Looks like there's a latent community here. We had so many registrations. We unfortunately had to close registration because of space limitations in the room. But we do think that there's seems to be an appetite for people across the communications and networking community and satellite aerospace communities to talk to each other. So we're gonna maybe try and set up an email list or something. There's an email which I think has been sent out or will be sent out pretty shortly by Philip Morris, who is the admin behind all of these nice things that you see here. And one of the questions there is about joining an email list. So if you are interested in keeping in touch, and looks like there's also a very strong comment section going on there. So certainly there's an active community out there. So let's try and capture that. And maybe we'll have something shortly again with another version of this. So thank you, everyone.
Are you going to put the slides of the presentation on the website?
That's the plan, at least. So we've asked the speakers, and I think many of the funding people have already sent on the chat, which I have downloaded personally, but others will follow up with other speakers, and we'll be putting all slides up on. And also, of course, you have the YouTube stream, which will be there for as long as Google is alive or YouTube decides to take this down. And yeah, so it'll all be there as a legacy of this workshop. So thank you for helping make this happen.
You.